Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. It begins with warmth. A gentle golden light caresses your closed eyelids and brushes your skin. You inhale, feeling the soft heat of sunlight that has traveled across empty space to reach you. In this quiet moment, the sunlight feels almost alive, a tender presence on a cool morning. You might take it for granted, this glow on your face, but it is the gift of an immense power. High above, the sun hangs in the sky, pouring out light and warmth in all directions. Now imagine following that warmth back to its source. Drift upwards, leaving the ground behind. The light grows brighter. Blue sky fades to black as you rise beyond Earth's atmosphere, and the sun's true face comes into view. A brilliant star burning in the dark. Here, hovering in space near the sun, there is no air to carry sound, only silence. Yet before you stretches an enormous sphere of glowing plasma, its surface a roiling ocean of fire. Tongues of flame and loops of energy dance at the edges, solar flares arcing outwards, but you hear nothing at all. This close, the sunlight is blinding and the heat is ferocious, but space itself remains eerily still and quiet. Inside the sun's core, countless atoms fuse each second, releasing prodigious energy. Photons born in that deep furnace begin a long random walk outward, bouncing through dense stellar material for ages before finally emerging at the surface as the warm light we know. When they break free, they rush into space at last, racing at light speed. Only about 8 minutes later, some will kiss a human face on a distant blue planet. But here at the source, you float in the glow of creation itself. The sun's surface seethes with granules and magnetic storms, yet from a few million miles away, it looks tranquil. A perfect, bright orb hanging in the void. A crown of wispy solar corona surrounds it, visible as a faint halo. Fine streams of charged particles, the solar wind, flow outward, but you cannot see them. Only feel their faint whisper, if you could hold out a hand. This star, so loud in its nuclear heart, offers its energy to the solar system in utter silence. You turn slowly away from the sun and begin a long spiral journey outward. The light at your back diminishes a little with each passing million miles. Ahead lies the domain of planets, tiny islands of matter circling the parent star. The first island appears very soon. Mercury, the innermost planet, emerges from the glare. Mercury is a little round world of rock and metal, so close to the sun that it's been baked bone dry. As you approach, you see a globe that looks strikingly like Earth's moon, grey, heavily cratered, and airless. Long ago, impacts pockmarked its surface with craters of all sizes, and there have been no winds or rains to soften them. Daylight here is harsh. The sun looms more than 3 times larger than it does in Earth's sky, and the ground under the sunward side blazes under intense heat. You can almost feel it radiating off the cracked regolith. The rocky ground expands and cracks from the scorching temperatures. But Mercury rotates extremely slowly. One day lasts 2/3 of its year. So one side broils in endless daylight, while the other side, long without sun, cools to frigid darkness. In the black sky above the sunlit surface, the stars are visible even at noon, because there is no atmosphere to hide them. If you could stand on Mercury at midday, the sun's fierce light would pour down from a pitch-black heavens. And when night finally falls many Earth days later, it brings a cold more intense than any winter, freezing the ground solid as the heat radiates away into space unimpeded. As you drift low over Mercury's surface, you notice bright streaks around some craters, rays of ejected dust from ancient impacts. You also see great curving cliffs, hundreds of miles long, that cut across craters and plains. These scarps formed as Mercury's interior cooled and shrank, wrinkling the surface like a dried apple. Mercury is astonishingly dense for its size. Deep below, it holds an outsized iron heart, a metal core taking up most of the planet's volume. That heavy core and the sun's gravitational grip keep Mercury locked in a strange dance. It spins 3 times for every 2 orbits around the sun. In Mercury's polar recesses, where the sun's rays never quite reach, there are deposits of water ice hidden in eternal shadow inside craters. It seems impossible, yet even at the sun's doorstep, frost can exist in the dark. Mercury is a world of extremes: blazing day, airless night, searing sun, and hidden ice. It is the innermost sentinel of the sun, a little cratered enigma racing around the star every 88 days. You leave Mercury behind, a tiny scorched globe receding into the brilliance, and journey outward to the next planet. As the sun's glare lessens a bit more, a pale yellow-white beacon appears ahead: Venus. From a distance, Venus is breathtaking, a perfect pearl of a planet, swathed in thick white clouds that reflect sunlight brilliantly. It outshines everything in the night sky, but the moon, a lovely evening star. Yet that beauty hides a deadly secret. Dropping down toward Venus, you penetrate its cloud layer and enter a smothering world of golden twilight. The atmosphere here is a dense broth of carbon dioxide with clouds of caustic sulfuric acid droplets. The further you descend, the darker and more orange the light becomes, tinted by the thick haze. Venus's clouds form an ever-present global blanket, so the surface knows nothing of stars or blue sky. Only a dim, diffuse illumination under eternal overcast. Deeper and deeper you go, and the pressure mounts. At the surface, the atmosphere presses down at 90 times the pressure of Earth's, like being 900 meters under the ocean. The air is a supercritical fluid, almost syrupy in its density. Here, a human would be crushed instantly. And the heat is astonishing. The temperature near the ground is hot enough to melt lead and zinc. The rocks themselves glow faintly dull red from the furnace-like environment. There is no water. Any that Venus once had boiled away eons ago in a runaway greenhouse inferno. In the dim light, you make out a barren landscape. Rolling plains of volcanic rock. Sharp-edged stones under an orange sky. The terrain is strangely quiet and still. No rain ever falls. No wind stirs at ground level. The air is too heavy. Only far above, at the cloud tops, do high winds race around the planet, shrouding it in fast-moving storms that never touch the hellish ground below. Volcanoes dot the surface, some enormous shield volcanoes bigger than any on Earth. Much of Venus appears to be covered in vast basaltic plains from ancient eruptions. In some places you see fields of strange domes and arachnoid patterns, volcanic landforms crushed and contorted by the intense pressures. The ground shows evidence of past lava flows and perhaps current volcanism, fresh-looking basalt, and signs that the planet may still be geologically alive. But if volcanoes erupt here, they do so in utter secrecy beneath the perpetual cloud deck, their red glow absorbed by the choking haze. The heat on Venus is unrelenting and nearly uniform across the planet, day or night. Venus turns so slowly on its axis, it takes longer to rotate once than to orbit the Sun, that a single Venusian day lasts almost 4 Earth months. But the thick atmosphere evens out the temperatures, carrying warmth to the night side. It is a world in slow motion, skies forever darkened by cloud, surface baking in constant dusk. For billions of years, Venus has known no relief from this self-made purgatory. Long ago, perhaps, it might have had shallow seas and milder air before something went terribly wrong. Now it stands as Earth's twisted sister, nearly the same size and composition as our home, yet completely inhospitable, a vision of a greenhouse nightmare. The only hints of anything gentle are far above, about 50 kilometers up. In the upper cloud layers, the temperature and pressure are nearly Earth-like. High in those clouds, strange streaks and patterns have been observed, perhaps just chemistry and droplets. But some have speculated about airborne microbial life surviving in the temperate heights, living in acid droplet clouds. It remains only a tantalizing idea. Leaving Venus, you ascend back through thick orange clouds that thin to bright white and finally break into clear space above. The planet's shining veil closes beneath you, hiding that toxic surface once more. You are glad to leave the crushing pressure and stinging acid behind. Out here above the clouds, Venus looks serene again. It is hard to imagine the inferno lurking below that placid cover. With a silent farewell to the morning star, you journey onward. The sunlight now is gentler, more golden, as you approach the orbit of Earth. Soon, a jewel appears in the blackness, a blue marble adorned with swirls of white. Our home, Earth, reveals itself in full sunlit glory, a sight to fill the heart with wonder. From space, Earth is a vision of vibrant color, deep sapphire oceans, bright tan deserts, verdant green-brown landmasses, and above them, swirling white cloud formations. A delicate film of atmosphere encircles the planet as a thin, glowing blue rim at the horizon. Compared to the harsh, airless moon or the choking blanket of Venus, Earth's atmosphere is a tender and life-sustaining mix, just thick enough to spread warmth and allow weather, transparent enough to let sunlight nurture the surface below. You descend toward the Earth, and as you slip into the atmosphere, you feel the first tug of aerodynamics, hear the faint whistle of wind. Thin, high air grows to a breathable breeze. Puffy white clouds drift below, casting soft shadows on the oceans. You pass through a layer of wispy cirrus and emerge over a vast expanse of ocean. Sunlight dances on waves that roll and break in white foam. The air is sweet and carries the scent of salt and living things. Seabirds wheel and cry beneath you as you skim just above the waters. Unlike any other planet in our solar system, Earth's surface is mostly liquid, an ocean world where life began in warm primordial seas. The blue expanse seems endless and calming. Moving over a coastline, you see green forests hugging the shores and brown mountains further inland, capped with snow. Rivers sparkle in the sunlight, winding from highlands down to estuaries, carving valleys over eons. In the forests and plains, every patch of Earth is alive, a tapestry of life forms in every shape, each contributing to the grand harmony of the biosphere. You sense activity and energy everywhere, the flutter of leaves in the breeze, the chirp of insects, the distant roar of a waterfall, perhaps even the murmur of human civilization if you listen closely. Faint hints of voices or engines far below, nearly lost in the vastness. Earth is alive both geologically and biologically. Its crust continually renews itself through plate tectonics. Continents drift imperceptibly, colliding to thrust up mountain ranges and pulling apart to create new ocean floor. Volcanoes occasionally pierce the surface, bringing up nutrients from Earth's depths, and earthquakes remind us that our planet's skin is restless. And Earth is alive in another sense. It hosts a biosphere that has transformed the air and land. Green plants inhale carbon dioxide and exhale oxygen. Animals do the opposite. Life and Earth dance together, each shaping the other. The atmosphere you breathe, rich in oxygen and balanced with nitrogen, exists only because countless tiny organisms in the ancient seas produced oxygen as a waste gas over billions of years. Now forests and phytoplankton maintain that balance. The result is air that allows both intense activity and gentle breezes, clouds and rain, climate and seasons. Earth sits at just the right distance from the sun, not too hot, not too cold, allowing water to remain liquid at the surface, cycling perpetually from ocean to cloud, to rain to river, and back to ocean. This endless water cycle weaves weather and nourishes life. On the day side, puffy white clouds gather over tropical seas, releasing afternoon showers. In the night, Thunderstorms flicker over equatorial lands, illuminating clouds from within with lightning's glow. Polar auroras shimmer occasionally at the highest latitudes, painting the sky with silent curtains of green and red light when solar particles strike Earth's magnetic field. High above, Earth's magnetic field forms an invisible shield, deflecting dangerous charged particles from the sun, ensuring the surface is not stripped of its atmosphere or sterilized by radiation. This magnetosphere funnels some particles to the poles, where they create those auroras, a gentle, beautiful side effect of our planet's protective embrace. Circling the Earth is its constant companion, the Moon. As you move around to Earth's night side, lit now only by starlight and the silver glow of the Moon, you gaze up from an earthly hillside at the lunar disk. The Moon hangs in the sky, airless and silent, shining by reflected sunlight. This grey orb has been a beacon for humans for as long as we have existed, its phases marking the passage of months, its gravitational pull quietly stirring our ocean tides. You decide to visit our Moon, rising off the Earth's surface once more and gliding toward that familiar cratered globe. In hours you arrive, settling down onto a vast lunar plain. The scene is otherworldly. The ground is covered in fine charcoal-colored dust, undisturbed save for ancient meteorite craters and, in certain spots, the faint tracks left by human explorers. Here on the Moon, the sky is pure black even when the sun is up. The harsh sunlight casts inky shadows among the rocks. You notice footprints pressed into the powdery soil, footprints left by Apollo astronauts half a century ago. They look as fresh as if made this morning. With no atmosphere here, there is no wind or rain to ever erase them. They could remain for millions of years, silent testimony to humanity's reach. The Moon's landscape is starkly beautiful in its simplicity. Rolling plains of solidified lava called Maria, lighter highlands densely cratered by impacts, and the pitch-black shadows inside deep craters near the poles where sunlight never shines. In some of those craters, scientists have discovered ice mixed with the soil, delivered by comets and preserved in the perpetual cold of shadow. You gaze back toward Earth, a blue marble now rising above the Moon's horizon. The Earth is many times larger in the lunar sky than the Moon is in Earth's sky, and it hangs almost motionless because the Moon keeps one face always turned toward us. A dazzling halo of blue and white, our home planet looks alive and fragile from here, suspended in space, half illuminated. It casts a gentle pale glow across the lunar ground. Earthshine, lighting the night portions of the Moon, just as moonlight illuminates Earth's night. The connection between Earth and its Moon is profound, gravitationally locked in an ancient dance, each affecting the other. The Moon's pull raises the ocean tides on Earth, and perhaps helped stabilize Earth's tilt over geological time, smoothing the seasons. And Earth's gravity, in turn, raised enormous tidal stresses in the young Moon that may have shaped its early volcanism. Climbing back into space, you leave the Moon's silent regolith and continue outward. You have now passed the Sun's first two inner worlds and Earth with its satellite. Next in line is Mars, the red planet, glowing with a rusty hue in the distance. Approaching Mars, you find it smaller than Earth, about half the diameter, and wrapped in a much thinner atmosphere. Its ruddy color comes from iron oxide, essentially rust, in the dust that covers its surface. Once you enter the Martian atmosphere, you realize how tenuous it is. Just a faint whisper of carbon dioxide gas, less than 1% the density of Earth's air. The sky here has a butterscotch tint, tinted by fine dust suspended high above. In the daytime, the sun is a bit dimmer and smaller than on Earth, its warmth far weaker in the thin air. You drift down to the surface near the Martian equator, landing on a broad reddish plain strewn with rocks. The ground is covered in reddish sand and dust that clings electrostatically to everything. In the far distance, a colossal mountain rises. Olympus Mons, the largest volcano in the solar system. Its huge bulk so wide and gentle sloped that from here you might not realize you're looking at a mountain at all, but it towers many kilometers above the surrounding plains. In another direction, you see a great canyon system cutting across the landscape, Valles Marineris, a chasm that would span from Los Angeles to New York if it were on Earth, and several times deeper than the Grand Canyon. It rends the Martian crust with steep cliffs and layered walls, colored ochre, gold, and red. This immense scar speaks of tectonic forces or something that nearly tore the planet apart long ago. The air is deathly still. Occasionally a light breeze may stir some dust, but Mars's atmosphere is usually eerily calm. Yet at times it can erupt. Global dust storms have been known to engulf the entire planet, turning the sky a tawny brown for months. But on this day, it is tranquil. The temperature is cool, near freezing at noon, but will plunge far below freezing after sunset. Overhead, the sky is a yellowish brown near the sun, fading to a deeper blue-gray at zenith. There are wispy clouds of ice occasionally, and in the late afternoon, you might even see a delicate streak of cloud catching the sun. Mars is a desert world, cold and dry. But as you wander, evidence of water is all around you in the shapes of the land. You float over an ancient river valley, now completely dry, its once sinuous channel carved into the rock. Long ago, water, actual liquid water, flowed here, possibly in rivers and lakes. You spot what looks like an old delta where a river met a basin, the telltale fan shape of sediment. And that great canyon, Valles Marineris, may have been enlarged by water flowing out from underground. Today, however, Mars is a freeze-dried world. The only water you see lies locked up as ice. Caps of bright white at the poles gleam against the rusty terrain, composed of water ice and carbon dioxide ice, dry ice, that grows and shrinks with the seasons. Just beneath the surface at these latitudes, a permafrost of ice extends for miles. The sun is setting now on Mars. In the west, the sun descends as a small bright disk, and the sky around it turns coppery. Curiously, just as the sun drops below the horizon, the sky directly above the setting sun glows a cool bluish tint for a few moments, a quirk of how the fine dust particles scatter blue light more efficiently when the light path is long. Twilight on Mars is blue. Soon, the first stars prick through the sky, and an intense cold permeates the thin air. In the darkness, you notice two tiny moons rising. Phobos, the larger, is a misshapen rock only about 22 kilometers across, looking more like a big asteroid than a proper spherical moon. It orbits Mars with dizzying speed, crossing the sky from west to east in just 5.5 hours. Deimos, smaller and farther, appears as a star-like point of light. These moons are likely captured asteroids, pilfered by Mars's gravity long ago. Phobos hangs so close that in some regions of Mars, it would appear to dart overhead multiple times each day. Its surface is dark grey and heavily cratered. A large crater named Stickney gives it a somewhat skull-like appearance. Someday Phobos will spiral inward and break apart or crash into Mars. But for now, the two potato-shaped moons silently circle their rust-colored master, witnessing the red planet's lonely desert sunsets. Mars feels like a world on the cusp, a once active planet, now largely asleep. Long ago, it had volcanoes that built towering mountains and water that carved channels through its soil. Something changed. The volcanoes grew quiet, the water froze or escaped, and the atmosphere thinned to nearly nothing. Now it waits, an enormous and silent desert, tinted red by the oxidized dust of ages. Still, it beckons us with its similarities to our own world: polar caps, day lengths and tilted axis that give it seasons like Earth's, though colder, and a geology that speaks of processes familiar yet extinct. In its soil and rocks, Perhaps microbial life once took hold in the wetter past. Perhaps even now some hardy remnants survive hidden beneath ground, clinging to warmth and moisture. Mars keeps its secrets for now, whispering them in dry winds that occasionally skip dust devils across the plains, dancing columns of dust that briefly snake upward before dissipating. You watch one of these dust devils swirl in the distance, tracing a delicate path and leaving dark streaks where it cleared the reddish dust off the surface below. Then it's gone, and stillness returns. You have now traveled roughly half the length of the solar system's planetary zone. Ahead lies the vast expanse beyond the inner rocky worlds, a domain of giants and mysteries. As you depart Mars, you traverse the boundary between the inner and outer solar system. The sun is smaller now behind you, though still bright. Moving outward, you enter a wide region populated not by singular planets, but by countless smaller bodies, the asteroid belt. This torus of debris stretches between Mars and Jupiter, filled with remnants from the solar system's formation. Contrary to Hollywood depictions, the asteroid belt is mostly empty space. The asteroids within are separated by hundreds of thousands or even millions of kilometers. You could drift through and likely never encounter one unless you deliberately navigated to it. But imagine you could see all these rocks at once, speed up time, or put them all before you. You'd behold a vast swarm of ancient mountain-sized boulders and smaller rocks, each tumbling in the sunlight, casting stark shadows on themselves. Some are solid metal, shiny nickel-iron fragments of long-destroyed protoplanets' cores. Others are porous rubble piles of rock and dust, only lightly held together by gravity. Most are irregular, cratered from countless collisions with their brethren. These are the leftovers that never formed a planet, perhaps due to the disruptive gravity of nearby Jupiter. You pass one of the largest asteroids, Ceres, a dwarf planet roughly 950 kilometers wide. From a distance, it looks almost spherical, a dull grey world with bright salty white patches gleaming within some craters. Those bright spots mark places where briny water or slush oozed up from Ceres's interior and deposited reflective salts upon evaporating, evidence that even this small body has or had a subsurface ocean, or at least pockets of liquid in its past. Ceres is a gentle world with a light gravity. Long ago, it may have been warm enough inside to differentiate into layers. Today it's cold, but still may hide slushy mud or ice deep down. As you glide low over one bright crater named Decatur, you see the ghostly shimmer of those salt deposits, remnants of cryovolcanism that happened within the last few million years, nearly yesterday on geological timescales. Ceres, quiet now, hints at activity not so very long ago. Farther on, you pass by an oddly angular rock. It's Vesta, another giant asteroid, with a huge gouge at its south pole from a titanic impact. That impact blasted out enormous quantities of debris. In fact, many meteorites that fall on Earth are pieces of Vesta, identified by their unique mineral signature. Vesta's surface is a patchwork of light and dark areas, ancient basaltic lava plains and brighter highlands. It almost became a planet. It has a core and mantle like one, but it never grew quite large enough. Scattered through the asteroid belt are countless smaller bodies, like little Ida with its tiny moon dactyl or metallic Psyche, shining faintly as it tumbles end over end. Occasionally, two asteroids have collided and shattered, and you see their fragments following similar orbits, family groupings of rubble slowly dispersing over eons. In this region, the echoes of creation and destruction linger on every scarred surface. It's serene now, but the belt's history is violent. The asteroids we see are the survivors of an early era of frequent collisions. Even today, once in a while, asteroids still collide, and the impact sends out showers of debris. Some of that debris might eventually wander inward as meteoroids and sometimes reach Earth, flaring as shooting stars or meteorites on the ground. Coasting outward through the asteroid belt The sun continues to shrink behind you. The inner planets are now tiny dots lost in a brilliant solar glare. Ahead, an entirely different kind of planet awaits, the first of the gas giants. Jupiter grows from a star-like point to a visibly disk, then to an immense striped globe dominating your field of view. You have arrived at the king of planets. Jupiter is staggering in its size. Over 11 Earths could be lined up across its face. As you come alongside it, you feel dwarfing humility before this banded colossus. Its upper atmosphere is patterned with broad bands of white, ochre, and reddish-brown wrapping around the planet. These are rows of clouds driven by powerful winds that roar east-west at hundreds of kilometers per hour in opposite directions for adjacent bands. The lighter bands, called zones, are higher clouds of ammonia ice, while the darker belts are deeper layers where other chemicals give ruddy and yellow hues. The boundaries between belts and zones are turbulent, with eddies and swirls where the opposing winds shear against each other. One feature stands out especially on Jupiter's canvas: the Great Red Spot, a titanic storm twice as wide as Earth. This oval tempest has been churning in Jupiter's southern hemisphere for at least 350 years, since humans first observed it through telescopes, and likely far longer. Within its brick red oval, winds howl counterclockwise around a high-pressure center, and ammonia clouds pile high. It is a cyclone of enormous proportions, its outer edges flaked by smaller vortices. As you hover above it, you see the spot's color has softened to a coral or peach tone nowadays, and it has shrunk somewhat compared to historical records. But it is still a vast, persistent hurricane beyond any earthly scale. We could drop our whole planet into it with room to spare. Lightning crackles elsewhere on Jupiter too. Near the poles, bright white thunderstorms erupt from deep water cloud layers, occasionally illuminating the cloud tops with brief flashes. Jupiter's atmosphere is dynamic and alive with activity, a ceaselessly roiling artwork of fluid physics. There is no solid ground for you to land on here. Jupiter is likely composed mostly of hydrogen and helium gas, with increasing pressure and density as you go down. If you descended through those clouds, the atmosphere would thicken into a hot soup, eventually into a fluid state, and deeper still perhaps into metallic hydrogen that conducts electricity like a metal. Far below that, somewhere in the crushing depths, may lie a dense core of rock and ice perhaps, but no human-made probe could survive long enough to reach it. Instead, you remain high in the atmosphere, skimming along the cloud tops at a safe distance. The view is magnificent. It's like floating above an unending cloud ocean, with rolling formations and whirls the size of continents. Long, snaking cloud bands trail around, and small oval storms, white or brown, dot the belts, each one a cyclone or anticyclone. High-altitude haze in places casts shadows on lower cloud decks. Over the poles, which were unseen by any human until recently, you would find swirling clusters of cyclones arranged in geometric patterns. Immense polar vortices, with unexpected symmetry, quietly rotating in the dim sunlight at high latitude. Jupiter is more than just a planet. It's almost a miniature solar system of its own. Circling around it are dozens upon dozens of moons, a retinue of diverse worlds bound by Jupiter's mighty gravity. 4 of those moons are so large and intriguing that they draw nearly as much interest as the planet itself. If you drift outward a bit to a vantage where you can see Jupiter's entire system, the 4 Galilean moons line up like tiny disks orbiting in the plane of Jupiter's equator. Innermost is Io, a moon about the size of our moon, but painted in vivid mottled yellows, oranges, and black. Io is the most volcanically active body in the solar system. As you approach Io, you notice strange blotches and sulfurous colors on its surface. Those are volcano calderas and deposits of sulfur compounds. Suddenly, on the terminator, the line between day and night, you catch sight of a towering plume, a volcanic eruption in progress. A fountain of sulfur dioxide gas and dust is blasting out of Io's surface, arcing high into space to an altitude of several hundred kilometers before the frost of space causes it to snow back down. Io's gravity is low, so these plumes form umbrella-like canopies, like giant blooming flowers of smoke. The moon's entire surface is constantly repaved by lava flows. Lakes of molten sulfur glow red in the dark, and fresh lava plains cool to dark crusts. Io's intense volcanism is powered by Jupiter's relentless tidal grip. The giant planet's gravity flexes Io's interior as the moon orbits, generating heat by friction and melting Io's insides. No impact craters are visible on Io. Any that form are quickly buried under new volcanic deposits. The air is extremely thin, just a wisp of sulfur dioxide, but enough to freeze at night and form a faint transient atmosphere by day. Io is a tortured world of fire and brimstone, literally a moon on fire under Jupiter's gaze. Next out is Europa, only slightly smaller than our moon. Europa's surface is strikingly smooth and bright, crisscrossed by long reddish-brown streaks like cracks on an eggshell. That analogy isn't far off. Europa is encased in a shell of water ice, perhaps 20 kilometers thick, and beneath that ice lies a global ocean of liquid water. It's hard to believe at first. You stand on a world so cold that ice is rock, yet beneath your feet is likely a deep saltwater sea kept liquid by tidal heating from Jupiter's pull. Europa's surface tells a tale of this hidden ocean. The network of streaks and cracks suggests that the ice crust is continually fractured and shifted by tides, and occasionally water or slush wells up through the cracks to resurface the moon. Hardly any craters mar Europa's surface, implying it is young and continuously renewed. At a few spots, you see what might be small plumes, geysers of water vapor, venting into space through fissures in the ice, evidence that sometimes the ocean below can communicate with the vacuum above. The sunlight here is weak, and the surface is bitterly cold, around 160 degrees Celsius. But the ocean below, sealed under the ice, might be a comfortable temperature, and likely completely dark, except perhaps for faint glow from any hydrothermal vents on the ocean floor. Yes, deep down, at Europa's rocky core ocean interface, tidal heating may drive undersea volcanoes or hot springs, providing chemical energy and warmth. It is tantalizing to imagine life there in the deep, perhaps simple microbes, maybe even complex organisms, living out of view in the black waters of an alien ocean. You run a hand over the ice. It's hard as granite at this temperature. Reddish-brown stains near cracks hint at salts or organic compounds brought up from below. Europa is silent, but it holds its secrets close. An ocean under ice, a possible cradle for life adrift in Jupiter's powerful embrace. Beyond Europa orbits Ganymede, largest of the moons. In fact, the largest moon in the entire solar system, even bigger than Mercury. Ganymede appears as a mottled grey-brown sphere with regions of dark ancient terrain and lighter, somewhat younger, grooved regions. It has clearly suffered countless impacts. Its dark areas are saturated with craters. But in the lighter areas, you see long parallel grooves, signs of past tectonic activity that somehow stretched and broke the crust, perhaps from internal upwellings or global expansion. Ganymede is a world of water ice and rock. Its surface is mostly ice, as hard as rock, peppered with craters whose ejecta splashed out bright rays of fresh ice. Like Europa, Ganymede too is believed to hide a subsurface ocean, though deeper below, a thicker crust of ice. And remarkably, Ganymede has its own magnetic field, the only moon known to have one, indicating it likely has a molten iron or iron sulfide core, creating a dynamo like Earth's. As you pass through Ganymede's vicinity, you might feel a slight tug and wobble in Jupiter's magnetic field, evidence of Ganymede's magnetic bubble embedded within the giant planet's magnetosphere. On Ganymede's surface, if you stood there, Jupiter would loom huge in the sky, many dozens of times larger in apparent size than our moon looks from Earth. Its banded face would be visible if the side of Ganymede you're on is facing Jupiter, perhaps with the great red spot discernible as a reddish oval. The sunlight here, 5 times weaker than at Earth, still provides ample daylight on the ice. At night, the sky is dark and full of stars, and Jupiter would be an awesome, softly glowing presence, lighting Ganymede's ground in a dim twilight whenever it hangs above the horizon. Farther out lies Callisto, the most distant of the Galilean moons. Callisto is a world that appears ancient, almost primordial, with a densely cratered crust of ice and rock that seems never to have been reworked by internal forces. Its entire surface is covered in overlapping craters upon craters, so densely packed that new impacts must obliterate old ones. The largest impact basins have concentric rings like ripples frozen in time, Valhalla and Asgard, enormous bullseye patterns from titanic collisions in the far past. Callisto's surface glints with countless tiny bright spots against a darker background. The bright spots are relatively fresh ice exposed by impacts, contrasting with the darker, dustier surrounding terrain that has been weathered by eons of micrometeorite bombardment and radiation from Jupiter. Beneath Callisto's heavily cratered crust, there may also lurk a hidden ocean, according to magnetic data from spacecraft. Even this seemingly inert moon might hold a liquid water layer deep below, sandwiched between ice layers. If so, it is likely heavily mixed with salts and ammonia, and perhaps it never interacts with the surface. Callisto does not exhibit signs of geological activity. It appears to be a relic from the early solar system, its face virtually unchanged for 4 billion years. Drifting above Callisto, you reflect that this moon is like a museum piece, preserving the record of the heavy bombardment epoch in the solar system's youth, unlike its sibling moons which have erased or repainted their surfaces through internal activity. Leaving Callisto, you have sampled the 4 great moons of Jupiter: fire, ice, and 2 shades of twilight between. Each distinct, each fascinating. But Jupiter has many more smaller moons too. Tiny irregular captured asteroids far out and closer in, a retinue of small inner moons shepherding a thin system of rings. Yes, Jupiter has rings as well, faint, dusty rings, discovered only when spacecraft flew behind the planet and saw sunlight forward scattered. These rings are not like Saturn's broad icy ones. Jupiter's are subtle, made of micrometer dust grains slowly spiraling inward. The dust likely comes from meteoroid impacts on the inner moons like Amalthea and Thebe, each impact kicking up debris that then orbits as a tenuous ring. You might not notice Jupiter's rings unless you catch them at just the right angle with the sun. Still, they form a gentle band of light hugging the planet's equator, a whisper of structure around the gas giant. Turning away from Jupiter, you venture onward. The sunlight now is much fainter than when you began, only a quarter of its intensity at Earth's orbit. Stars crowd the sky as the ambient glare of the sun lessens, but ahead, another jewel awaits: Saturn, Lord of the Rings. Even from afar, Saturn captivates. Its pale golden globe is encircled by a magnificent system of bright, shining rings that span hundreds of thousands of kilometers. As you approach, the rings resolve into countless individual slabs of ice and rock, all orbiting in a flat plane like a celestial vinyl record. Saturn itself is a gas giant slightly smaller than Jupiter, with a more delicate hue. Bands of butterscotch, cream, and grey slide gently around its atmosphere. Its features are more muted than Jupiter's violent contrasts. But Saturn too has storm systems and high-speed winds. A broad, hazy belt girds its equator, and near its north pole you find a strange geometric wonder, the famous hexagon. It is a 6-sided pattern in the cloud tops at the pole, perhaps caused by the peculiar dynamics of a standing wave in the atmosphere. At Saturn's center, unseen below the clouds, lies a smaller core of heavy elements. But like Jupiter, Saturn has no solid surface at its cloud tops, just a gradual transition from gas to fluid. Saturn is less dense than water. In theory, If you had a bathtub big enough, Saturn would float. Yet it is the rings that draw your eye above all. You glide just above the ring plane, skimming the outer edge of the main rings. Stretched out below you is an almost flat expanse of icy particles. Some are grains of dust, others boulders the size of a house. They shine brilliantly in the sun, like countless diamonds on black velvet. The rings are astonishingly thin, in places only tens of meters thick, essentially two-dimensional when seen edge-on, though tens of thousands of kilometers in radial extent. Gently, you dip down into a gap between ring sections. Around you, ice chunks tumble slowly. If you were very quiet, you might even hear the tinkling of tiny impacts as particles collide softly or clump together briefly. Saturn's rings are mostly pure water ice, which is why they gleam so brightly. They likely formed from the breakup of a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. Now these countless fragments spread out in their orbits, sculpted by gravity into several distinct ring zones, divided by thin gaps. Some gaps, like the Cassini division, are maintained by the gravitational influence of Saturn's moons. Small shepherd moons like Pan and Daphnis carve narrow channels, their gravity herding ring particles and creating sharp edges and waves in the rings. Looking down at Saturn's rings from above is one of the most sublime views in the solar system. You see delicate spiraling density waves, like ripples or grooves in a vinyl record, caused by orbital resonances with moons further out. You see subtle color differences. The B ring is brilliant white, the C ring more dusky and translucent. Sometimes you see fleeting spokes, ghostly radial features that appear and dissipate, perhaps caused by electromagnetic effects, levitating fine particles temporarily above the ring plane. The rings cast a broad shadow on Saturn's cloud tops, a series of dark bands across the planet's face. Conversely, on the night side of Saturn, the rings reflect sunlight and cast a soft illumination, so that Saturn's night side is never completely dark when the rings are in sunlight. Yet for all their glory, Saturn's rings are transient on geological timescales. Already, ring material is slowly raining down onto Saturn, pulled by gravity and dragged by magnetic fields. It's estimated that in another 100 million years or so, the main rings may become thin and eventually vanish, either accreted onto Saturn or dispersed into space. We are lucky to live in an epoch when Saturn wears such magnificent rings. They may be a relatively recent adornment, and one day they will dissipate. But in this moment, as you float among them, they appear timeless and serene, a cosmic masterpiece of natural sculpture. Emerging from the rings, you turn attention to Saturn's family of moons. At least 82 moons circle Saturn, and more continue to be discovered. They range from tiny, irregular chunks a kilometer across to the giant Titan, second largest moon in the solar system. Each moon has its own character. Let us visit a few of the notable ones. First and foremost is Titan. As you approach Titan, you see a hazy orange globe, the only moon in the solar system with a substantial atmosphere. In fact, Titan's atmosphere is thicker than Earth's, made mostly of nitrogen with a touch of methane. It completely hides the surface from visible sight. You descend through this thick orange air, and at around 50 kilometers up, you pass through a layer of methane clouds. A gentle rain of liquid methane might be falling from some of these clouds, not water, which is frozen as hard rock on Titan, but methane, which at Titan's frigid 180 degrees temperature can exist as a liquid. Breaking through the cloud deck, you reach the surface and settle gently onto an open plain near a lake. Yes, Titan has lakes, not of water, but of liquid hydrocarbons. Before you, stretching to the horizon, is a mirror-like expanse of liquid methane and ethane, something like a primordial earthly lake, but under an alien starless sky. The sun here is a feeble yellow point, smothered in haze, so it's a dim twilight at noon. Across the liquid surface, you see the reflection of Saturn's distant glow in the hazy sky above. Though if Saturn is above the horizon, it would only appear as a pale light smudge due to Titan's thick atmosphere. Walking on Titan would be strangely pleasant in some ways. The thick atmosphere and low gravity give it a surface pressure similar to Earth's, and gravity only 1/7 of Earth's. You could actually strap on wings and fly in the dense air if you ran and flapped hard enough. But the temperature is unimaginably cold to us, and you'd need a heated suit to survive, not to mention an oxygen supply. The landscape around you on Titan might look surprisingly familiar in form. You see what appear to be river channels carved into the icy ground, leading to this lake, indeed named Kraken Mare. Rounded pebbles of water ice and solid hydrocarbons lie at your feet, smoothed by flowing liquid. There are even gentle waves on the lake's surface when the wind picks up. At the shore, a sludge of organic rich mud, a bit like wet sand made of plastic, squelches underfoot. Titan's atmosphere, laden with smoggy hydrocarbons created by sunlight-driven chemistry high above, deposits a constant drizzle of complex organics onto the surface. Over millions of years, Titan's surface has accumulated a wealth of carbon-rich compounds, the building blocks of possible biology, waiting perhaps for a spark of life. The air has a hint of aroma if you could smell it through a filter, perhaps a tang of hydrocarbons, akin to gasoline mixed with fainter, sweeter notes from other organics. Titan's world is like a deep-freeze laboratory of prebiotic chemistry, possibly reminiscent of early Earth's chemistry, but at cryogenic temperatures and without liquid water. Mountains of rigid water ice, hard as rock, rise in the distance, softly rounded by the thick atmosphere's lack of erosive power beyond the occasional methane rain. A low sun hangs in the perpetual haze. Daytime is a dusky affair, and as night falls, the clouds and haze block any stars. But occasionally, if the sky clears enough or in certain infrared transparency windows, the majestic presence of Saturn might faintly appear, huge and ghostly, occupying a broad region of Titan's sky, a pale source of light far more subdued than our moonlight back on Earth. Lightning is rare on Titan, as the atmosphere lacks strong convection generally, but who knows? Perhaps a rare thunderstorm could flicker in the distance over one of the hydrocarbon seas, briefly illuminating the alien shoreline. Titan quietly reminds us of Earth in mirror form, an active cycle of liquids, but made of methane. A thick atmosphere, weather, lakes, rivers, maybe even cryovolcanoes that erupt cold mixtures of water and ammonia from Titan's interior. It is a dynamic and complex world, all its own, one that could perhaps harbor very strange life that uses liquid methane instead of water. If such life exists, it would metabolize and move in extreme slow motion due to the cold, but it would find Titan a comfortable home. Next, you bid Titan farewell and venture to tiny Enceladus, another of Saturn's remarkable moons. Enceladus is tiny, only about 500 kilometers across, but brilliantly bright. Its surface is fresh, clean ice reflecting almost all the sunlight. As you orbit over Enceladus's southern hemisphere, you witness a breathtaking sight. Multiple geysers of fine icy mist spraying out from long tiger-stripe fissures near the South Pole. Enceladus is literally a cosmic fountain. These plumes are composed of water vapor and microscopic ice particles being vented from its interior ocean out into space. The jets feed a large diffuse ring around Saturn, the E-ring, with their ejected material. You fly through a plume, it's unavoidable, as they shoot hundreds of kilometers up. For a brief moment, your spacecraft's windows accumulate a fine frosting as the water vapor hits and freezes. Sampling the vapor would reveal salty water with organic compounds, essentially bits of the subterranean sea of Enceladus. Beneath the surface of this small moon lies a liquid water ocean sandwiched between the rocky core and icy crust, kept warm by tidal flexing from Saturn and perhaps radioactive decay. The plumes erupt through cracks in the ice, likely on the ocean floor. Hydrothermal vents add heat and minerals to the water, which then travels upward and escapes at the cracks. You descend towards one of those long fissures, known as Damascus sulcus, and peer into a bluish trench from which a mist continually emanates. At the edges of the trench, the ground is stained with deposited frost and possibly simple organics from the ocean spray. Surrounding terrain is relatively young, few craters, and marked by curving fractures and ridges. Enceladus's environment is like a natural spa of the solar system. Under its ice, warm water and perhaps life-sustaining chemicals brew and belch out gracefully into space. This moon, tiny as it is, has become one of the prime targets in the search for extraterrestrial life. One can imagine organisms around those hypothesized hydrothermal vents in Enceladus's ocean, feeding on mineral-rich fluids, living in total darkness, but thriving in warmth provided by Saturn's tidal energy. As in Europa's case, we have yet to confirm life, but all ingredients are there. Even in deep space far from the sun, life might find havens where energy and liquid water exist. Enceladus orbits within Saturn's faint E-ring, which it maintains. When sunlight streams through the E-ring at just the right angle, you see a diffuse glitter around Saturn, billions of tiny ice grains catching the light. Some of those grains will eventually fall back onto Enceladus's surface like fresh snow, keeping it bright. Others escape Saturn's gravity or fall into Saturn eventually. In effect, Enceladus is a little icy comet continuously active around Saturn. Another notable moon is Iapetus, which you visit next on your Saturnian tour. Iapetus is half bright ice, half dark as coal. As you approach, you notice its striking two-tone appearance. One hemisphere, the leading face of its orbit, is coated in dark material, making it look like a yin-yang symbol. The other trailing side is bright white ice. Iapetus also has a bizarre equatorial ridge running most of the way around the moon's center, like a walnut seam, making it resemble a piece of a giant shell. This ridge is up to 13 kilometers high in places. No one knows exactly how it formed, perhaps long ago rapid rotation or a collapsed ring that settled on the surface. You pass over a region known as Cassini Regio, the dark hemisphere, and the ground below looks like asphalt sprinkled with frost. Craters on the dark side have bright rime along their rims, where lighter subsurface ice was exposed by impacts. It is a world of stark contrast, quietly circling Saturn at great distance, far beyond Titan. The dark coating is likely a thin layer of organic rich dust, perhaps swept up from outer irregular moons or from Phoebe, an outer moon of Saturn, and deposited on Iapetus's leading face like bugs on a windshield. This deposited material warmed slightly in sunlight and sank into the ice, creating a runaway effect of sublimating the bright ice and leaving behind more dark stuff, thus darkening that side further. Meanwhile, water vapor redeposited on the colder trailing side, making it even brighter. Thus, Iapetus became an extreme study in albedo dichotomy. Time would fail to speak of all Saturn's moons. The tumbling Hyperion, shaped like a sponge, chaotic in its spin, or tiny Mimas, with its huge crater resembling the Death Star, or Enceladus's siblings Tethys, Dione, and Rhea, each with its own pattern of cracks or craters, or ancient rings of frozen impact basins. Saturn's system is a rich archipelago of worlds, each worthy of exploration. But the cosmic clock urges you onward to the next realm beyond Saturn. Past Saturn, the sunlight dims further. The warmth of the inner solar system is far behind. Now you enter the domain of ice giants. First comes Uranus, a pale cyan orb spinning on its side. Indeed, Uranus's axial tilt is about 98 degrees, meaning it essentially rolls around the sun like a ball. When you arrive at Uranus, you find a world that at first seems subdued. Its turquoise atmosphere is almost featureless to the casual glance, just a slight shading from turquoise to deeper teal toward the poles. But careful inspection reveals faint banding and occasional white cloud streaks, likely methane ice clouds high in the atmosphere. Uranus has a faint haze that gives it its uniform appearance. This sideways planet has peculiar seasons. Because it's tipped so extremely, each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness, since one Uranian year is 84 Earth years. Right now, say, it might be that the North Pole is in full sunlight, a bright cap, while the South Pole is in a long dark winter. This tilt might be due to a cataclysmic collision in Uranus's early history that knocked it over. The consequence is extreme but weirdly static seasons. At solstice, one hemisphere bakes while the other freezes in darkness. However, bake is a relative term here. Even the sunlit pole's atmosphere is frigid, around 200 degrees C, and strangely, Uranus exhibits very little internal heat flow. Unlike its neighbor Neptune or the gas giants, Uranus's interior does not emanate significant extra heat, leaving its atmosphere relatively calm and cold. As you get closer, you notice Uranus is encircled by a set of thin, dark rings. They are much narrower and darker than Saturn's, composed of dark reddish material, likely tholins or radiation-darkened organics on ice. There are about 13 known rings, all quite faint, discovered in 1977 when they occulted a star. They appear as narrow charcoal black hoops around the planet's equator, which is tipped 90 degrees from its orbital plane. So the rings are often seen nearly face-on from the Sun's perspective, alternately showing us their broad face or edge depending on Uranus's position in its orbit. You also spot at least a few small moons embedded among those rings, shepherd moons that keep the ring particles corralled. Uranus has a retinue of at least 27 moons known. The larger ones are intriguing icy worlds themselves: Titania, Oberon, Ariel, Umbriel, and Miranda. Let's briefly visit one or two. Miranda is the smallest of the major moons, but perhaps the strangest. Its surface looks cobbled together from mismatched pieces. Part of it is old, heavily cratered terrain, but then there are bizarre regions that look like no other place, with huge fault canyons up to 20 kilometers deep, chevron patterns of ridges and troughs, and areas that seem almost like they were shattered and reassembled randomly. It's as if Miranda was broken apart by an ancient impact and weakly reformed into a jumbled mosaic. The gravity on Miranda is so low, less than 1% of Earth's, that you could easily hop off a tall cliff and not fear a lethal fall. You would drift down gently. In fact, off Miranda's cliffs, one of which, Verona Rupes, is touted as the tallest known cliff in the solar system, about 20 kilometers high, an object could take many minutes to drop to the bottom. Ariel and Umbriel are mid-sized moons, one bright and one dark. Ariel shows many signs of past geologic activity, a network of valleys and smooth plains that suggest internal ice melted and repaved parts of the surface in the past. Umbriel is darker, an old and shadowed world with many craters and a mysterious bright ring on one crater floor like a frosty deposit. Titania, the largest, shows long canyons and faults too, hinting it was once somewhat active. All these Uranian moons orbit in the planet's equatorial plane, which means they too are flipped on their side relative to the Sun. So at solstice, one hemisphere of each moon is in continuous sunlight, and the other in darkness for years, just like Uranus itself. One can imagine bizarre effects of such prolonged day-night cycles on any potential volatile ices, maybe subtle migration of surface frost from the hot pole to the cold one. The environment out here is hushed and dim. Uranus's magnetosphere rotates on its side, resulting in complex interactions with the solar wind. As you depart the Uranian system, you note the aquamarine planet receding, encircled by its thin black rings and tiny spark moons, a silent, tipped-over world doing its slow roll around the Sun. Pressing farther out, you reach Neptune, the outermost known major planet. Neptune is the twin of Uranus in size and composition. Both are ice giants, with a mix of hydrogen, helium, and a higher proportion of water, ammonia, and methane ices in their interiors. But Neptune has a much more dynamic personality. As you approach Neptune, you see a rich azure blue planet with a few obvious features. There is a dark oval storm system reminiscent of Jupiter's red spot, the Great Dark Spot, though by now it might have dissipated since it was last seen by Voyager 2 in 1989. Neptune's dark spots come and go. You also see high-altitude bright white clouds, likely methane ice cirrus, casting shadows on layers below as they race around in Neptune's fierce winds. Indeed, Neptune holds the record for the fastest atmospheric winds in the solar system, with jet streams up to 2,000 km/h. How such ferocious winds arise on a planet receiving so little solar energy is still somewhat mysterious, but Neptune does radiate more internal heat than Uranus, fueling more weather. At Neptune's south pole, the one Voyager saw sunlit, a haze of orange smog was observed, perhaps some warming effect creating slight color change. Neptune too is tilted, about 28 degrees, similar to Earth's 23 degrees. So it has seasons, though each season lasts over 40 years given its 165-year orbit. Currently, perhaps the southern hemisphere is transitioning to darkness and the north coming into light. Observations from Earth's telescopes in recent years have shown that Neptune's clouds and storm activity wax and wane with seasons. For instance, more frequent dark spots and bright clouds at certain times. Like all gas ice giants, Neptune has rings as well. Neptune's rings are faint and reddish, and not uniform. Intriguingly, they have clumpy segments called ring arcs, particularly in the outermost Adam's ring. These arcs, named Liberté, Égalité, Fraternité, and Courage, puzzled astronomers because orbital mechanics say a continuous ring should spread out evenly, yet here, material clumps in certain sections. It's now thought that one of Neptune's moons, Galatea, herds these arcs gravitationally and keeps them from dispersing. Neptune has a retinue of moons, 14 known. The standout is Triton, one of the most fascinating moons in the solar system. When you arrive at Triton, Neptune's largest moon, you are met with an icy pinkish landscape. Triton orbits Neptune in a direction opposite to Neptune's rotation, a retrograde orbit, strongly suggesting it was a captured Kuiper Belt object rather than forming alongside Neptune. Because of this, Neptune's gravity is gradually pulling Triton inward. In some distant future, billions of years, Triton will either break apart into a ring or crash into Neptune. But not yet. Triton's surface is extremely cold, about 235 degrees Celsius, cold enough that nitrogen exists as frost and methane and carbon monoxide ices decorate the surface. Voyager 2's flyby revealed Triton's surface to be surprisingly complex and young in places. Large swaths of terrain with few craters, indicative of recent reshaping. At Triton's south polar region, a cap of faint pinkish nitrogen ice and methane ice lay with dark streaks across it. Those streaks, it turned out, were the fallout from geysers. Yes, Triton too has active geysers. When sunlight in the southern spring warmed transparent layers of frozen nitrogen, it likely caused sublimation and pressure buildup beneath, eventually erupting as geysers of nitrogen gas, carrying dark dust up to 8 kilometers high. The gas then blew downwind, depositing the dust in dark plumes that extended many tens of kilometers. You might witness one of these right now. Imagine standing on Triton's endless plain dubbed the cantaloupe terrain, because its texture looks like a cantaloupe rind, likely due to diapirs or rising blobs of ice causing the surface to deform. In the distance, a whisper-quiet geyser begins. An invisible jet of nitrogen gas lofts, a column of fine, dark particles. Because Triton's atmosphere is extremely tenuous, only a fraction of a pascal of pressure, you cannot hear anything, but you see a faint, hazy plume rising and drifting sideways ever so slowly. The sky is a pale peach near the horizon from the thin haze, and above it quickly darkens to black. The sun is weak, barely providing any heat. You can feel the deep cold even in your insulated suit. Triton's terrain has variety. The Cantaloupe region, the polar caps, and weird zones of what look like melted terrain, possible cryovolcanic landscapes where slush may have erupted in the past and refrozen into smooth plains. You move over a region called Leviathan Patera, an irregular walled depression that could be a collapsed caldera of an ice volcano. Near the terminator line, where day meets night, you notice the glint of starlight on what appears to be smooth, reflective surfaces. Could these be lakes of liquid nitrogen? Possibly not stable, but maybe transient pools when seasonal heating allows some melting of the nitrogen ice. Neptune's other moons are far smaller. Nereid, Proteus, a large, irregular dark chunk, heavily cratered, that Voyager imaged, nearly filling its Roche limit around Neptune but stable, and several newly discovered tiny ones. But none approach the interest of Triton. Now you have traversed all 8 major planets from the bright furnace of the Sun's vicinity to the twilight realm of Neptune. Beyond Neptune, the formal boundary of the classical solar system, there lies the vast expanse of the Kuiper Belt. Once, Pluto was considered the 9th planet, but we now know it as one of the largest members of this belt of icy bodies at the fringe of the Sun's influence. Your journey continues outward, and soon you encounter Pluto, shimmering dimly with a faint beige-white color mottled with darker patches. Pluto is a small world, only about 2/3 the size of our moon, but it is rich in character. As you draw near, you see an enormous bright heart-shaped feature dominating one hemisphere. This heart is Tombor Regio, and its western lobe is a vast basin of nitrogen ice called Sputnik Planitia. This frozen plain is unlike anything you've seen. It's a smooth, cream-colored expanse with subtle cellular patterns on it. Those cells are outlines of convection within the nitrogen ice. Yes, the frozen nitrogen here, soft as wax, is slowly churning over eons, like a gigantic lava lamp of frost. This convection constantly renews the surface, erasing craters, so Sputnik Planitia is essentially craterless and very young in appearance. You skim low over it and realize you're flying above a frozen sea of molecular nitrogen. In places, you see pits where nitrogen has sublimed away. In others, where perhaps a recent impact delivered a jolt of heat, the nitrogen might have melted and refrozen. At the edges of the heart-shaped plain, you find towering water ice mountains named Hilary Montes and Norgay Montes. Some peaks reaching 4 to 5 kilometers high, thrusting jaggedly above the plains. Water ice on Pluto is as strong as rock and forms the bedrock that the softer ices, nitrogen, methane, carbon monoxide, overlay. These mountains may be uplifted blocks of water ice or the rims of an ancient impact basin, now filled by Sputnik's ice. North of the heart lies a rugged highland of older ice, cut by canyons and dotted with crater depressions. To the east, a vast region of reddish-brown hues called Tartarus Dorsa is covered in strange aligned ridges like scales or bark. They call them bladed terrain, likely huge sublimation sculpted cliffs of methane ice. Perhaps where volatile ices have preferentially vanished, leaving behind the harder stuff in blade-like formations oriented by sun exposure and wind. On the dark anti-heart side of Pluto lies a large, diffuse, dark region called Cthulhu Macula, a possibly organic-rich expanse, older and heavily cratered in spots, with a draping of dark tholin, complex organic molecules created by UV light acting on methane, giving it a ruddy charcoal color. Sunset on Pluto comes swiftly. The sun is just a brilliant star here, providing twilight-level illumination even at noon. As darkness falls, the sky reveals something wondrous, a soft blue haze around Pluto, surprising for such a small world. This haze is made of layered photochemical smog. Sunlight, even weak, triggers chemical reactions in the thin atmosphere, converting methane into complex hydrocarbons, which then condense into tiny particles. creating a delicate, multi-layered haze up to 200 kilometers high. The haze is visible when the sun is low, scattering blue light, giving Pluto's limb a cerulean halo. Through that haze, you might see the pinprick of the sun setting and also another pinpoint shining. That would be Charon, Pluto's largest moon. Charon is half the diameter of Pluto, so big compared to Pluto that the two orbit each other around a point in space between them. One could call Pluto-Charon a double dwarf planet system. They are tidally locked to each other, always showing the same face to one another as they twirl in a 6.4-day dance. You decide to pay Charon a visit, drifting across the 20,000-kilometer gap separating them. Charon is grayish, with a dark reddish polar cap. A cap that likely comes from gases escaping Pluto and getting trapped and frozen onto Charon's pole during winter, where radiation then chemically alters them into red tholins. Charon's surface shows an expansive system of chasms, a giant belt of fractures that wraps around, indicating that at some point, Charon's interior water may have frozen and expanded, cracking the crust. There is a prominent large crater with bright rays near the equator, called Arakoth, impact by some, though unofficial, which hints that beneath any weathering, Charon's water ice is relatively clean and bright when excavated. On the far side of Charon, which we did not see via spacecraft, presumably more craters dominate. Charon has no atmosphere to speak of, so its surface is static and dead-looking, but still fascinating as a record of what goes on at the solar system's edge. Looking back at Pluto from Charon, you see Pluto's hazy silhouette occulting the distant sun, and a ring of light around Pluto's limb, an atmosphere and haze backlit, glowing a faint gold and blue. This reminds you that even these tiny worlds have complexity and beauty. Pluto's atmosphere is extremely thin, about 100,000 times thinner than Earth's at surface. Mainly nitrogen with some methane, but it is escaping gradually as Pluto can't hold it forever. In Pluto's sky during day, that atmosphere would likely produce a blue tint, and one could even see a faint sunbeam or twilight after sunset due to the haze. Departing Pluto and Charon, you now sail truly into the unknown dark. The sun becomes just one star among many, albeit the brightest. You have entered the Kuiper belt fully. Here exists a vast collection of icy bodies, leftover planetesimals from the solar system's formation, preserved in cold storage. Many of these are small, irregular chunks, only a few kilometers wide, but some are quite large, Pluto's size and bigger. In fact, not far beyond Pluto in a cosmic sense lies Eris, a dwarf planet slightly smaller than Pluto, but more massive, with an even higher density, suggesting less ice fraction. Eris is so far from the Sun that its atmosphere, if it has one, is entirely frozen onto its surface most of the time. When nearer perihelion, perhaps a thin layer of atmosphere sublimates. Now at aphelion, likely it's frozen solid. Eris's surface is extremely reflective, perhaps from a coating of nitrogen or methane ice, making it one of the brightest objects in the Kuiper belt. There are also Haumea, an elongated, rapidly spinning dwarf planet with a weird shape and a family of collisional fragments trailing it. Makemake, another bright reddish dwarf planet slightly smaller than Pluto, and numerous others being discovered each year. The Kuiper belt extends from about 30 AU, Neptune's orbit, out to roughly 50 AU in a broad torus around the Sun's ecliptic plane. The population here moves in leisurely orbits around the Sun, taking hundreds of years to complete one circuit. Occasionally, gravitational nudges, perhaps from Neptune's past migration outward, have scattered some objects into eccentric or inclined orbits. Some cross Neptune's path, like Pluto, a resonant KBO locked in 3-2 resonance with Neptune. Others have been flung into even more distant orbits. As you continue outward, you pass countless unseen worlds. One such world presents itself in your path, a contact binary shaped like two lumpy spheres stuck together, resembling a snowman. This is similar to Arakoth, which New Horizons visited in 2019, likely a primordial object that formed by the gentle merger of two separate bodies. Its surface is very red from organic compounds, and it has no craters or geologic activity. It's a frozen time capsule from the birth of the planets. Such objects abound out here. Now the Kuiper Belt's outer edge appears. The density of large bodies thins out beyond about 50 AU. You are entering now the deep freeze, the realm of the comets. Out here, the sun is but one of billions of stars in the sky, and the warmth and light are feeble. This is the beginning of the Oort cloud, though at first perhaps better to say the scattered disk, a transitional region with objects on very elliptical or inclined orbits, which sometimes bring them far out, hundreds of AU, before returning toward the sun. You might pass one such traveler, perhaps a comet nucleus quietly drifting at aphelion, building up a dark crust of complex organics as cosmic rays process its ices over eons. At this distance, it is just an inert black potato a few kilometers across, waiting until one day a stellar perturbation or gravitational resonance nudges it onto a trajectory inward, where it will sprout a glowing coma and tail and be reborn as a comet, blazing in the inner solar system's skies. But beyond even these distant scattered objects lies the true boundary of the sun's kingdom, the Oort cloud. It is not a flat belt, but a vast spherical swarm of countless icy bodies surrounding the solar system in all directions. A shell of potential comets extending perhaps as far as 100,000 AU, nearly 1.5 light-years, from the sun. This region is mostly empty space, with objects tens of millions of kilometers apart, but within it reside perhaps trillions of comets. These are ancient leftovers from the formation of the outer planets that were flung out here by gravitational interactions long ago, or they are outer solar nebula condensations that never coalesced into larger bodies. Here, the sun's gravity is so weak that passing stars, or even tides from the Milky Way's mass distribution, can perturb or dislodge these comets. You find yourself floating in the darkness between stars. The sun is a very bright star behind you, but no longer overwhelmingly so. You can even look straight at it without shielding now, as it's barely brighter than Venus as seen from Earth, just a point of intense light. Out here, in the silence and darkness between the stars, as a NASA text once described the Oort cloud, you have reached the threshold of interstellar space. The icy nuclei of comets drift like sleepy moths around a porchlight, as one poetically put it, the porchlight being the distant sun, now just one star among many. Pick one such Oort cloud object, say, an untouched comet nucleus named perhaps after some catalogue number. It is an irregular body a kilometer or two wide, surface pitch black with some reflectivity, maybe only a few percent. It might have a crust of tar-like organics covering a matrix of ice and dust inside. It has been in deep freeze for 4.5 billion years, nearly unchanged since the time it formed close to the sun, before being ejected to the fringe. Occasionally, over the millennia, a passing star's gentle tug perturbs its orbit slightly. Most times, it remains bound to the sun, but sometimes, rarely, such nudges send an Oort cloud body falling inward as a long-period comet. Perhaps one day, this particular one will do so and delight future skywatchers with a bright tail. At the moment, however, here at roughly 30,000 AU from the sun, you are effectively beyond the heliosphere. In fact, you likely pass the heliopause, where the solar wind's influence yields to the pressure of the interstellar medium, back around 120 AU, a tiny fraction of the distance to the Oort cloud's far edge. That boundary is where Voyager 1 and 2 transitioned into true interstellar space in recent years. Now you are well beyond that, immersed in the sparse interstellar gas of our galaxy. Charged particles from the sun no longer dominate. Instead, cosmic rays, high-energy particles from distant stellar events, roam freely. Magnetic fields from the galaxy thread through space, only slightly perturbed by the sun's faraway presence. As you drift still outward, even the Oort cloud becomes tenuous. Eventually, at around perhaps 100,000 to 200,000 AU, about 2 to 3 light-years, the sun's gravitational grip on comets is at its limits. You are now truly in between the stars. It is dark. Dark beyond any night you experience near Earth, because here no nearby sun lights any sky. Yet, it is not pitch black. Look around. The Milky Way galaxy is a glorious band across the sky, far richer and brighter than from Earth because there is no atmosphere or light pollution. You see the combined glow of billions of distant stars in that band. You also see many individual stars too, brilliant blue-white ones, closer yellow ones, distant red ones. One of those stars, shining with a steady golden light behind you, is the sun as seen from here. Surrounding it, if you squint, you might just detect a very faint spherical cloud of comets reflecting its light weakly. The sun's aura of Oort cloud. Take a moment in this deep space to consider scale. It took light about a year to travel from the sun to your current position. The nearest star to the sun, Proxima Centauri, is still about 3 light-years further on. The emptiness is profound, but not absolute. There are wisps of interstellar gas and dust. You might encounter a diffuse molecular cloud, a region with slightly higher density of hydrogen molecules and dust, perhaps the birthplace of future stars. Out here, as you cross into the domain of the galaxy, you can almost feel the transition. Your spacecraft's instruments detect a change in the charged particle population. Galactic cosmic rays are the main contributor now. You are now in the interstellar medium, the thin soup of gas, dust, and cosmic rays that fills the space between stars and makes up much of the volume of the galaxy. If your eyes could see in radio or other wavelengths, you might notice the subtle glow of the cosmic microwave background in all directions, or emissions from distant nebula. But visually, it's the stars and the dark that command attention. Now your perspective begins to widen. With the sun now just another star behind you, you turn your gaze to the Milky Way as a whole. Imagine rising above the plane of the galaxy, which requires magical rapid travel on your part, beyond realistic speeds. But in this thought journey, you can transcend such limits at will. As you gain a bird's-eye view of our galaxy, its structure emerges. A majestic spiral disk with arcing arms of starlight and dark ribbons of dust. The sun resides in a minor spur between major arms, about 27,000 light-years from the galactic center. From above, you locate the sun's position, not marked by anything obvious, just one G-type star among billions, currently in a small local arm segment called the Orion Arm or Orion Spur that connects the Sagittarius and Perseus arms. If you mark it mentally, you can trace the sun's slow orbit around the galactic center, one circuit every 230 million years or so. The galaxy's disk is a flat glowing storm of stars, gas, and dust, roughly 100,000 light-years across. The central region is a swollen bulge of older yellowish stars, within which lies the very hub, a mysterious bright radio source known as Sagittarius A, which is the location of a supermassive black hole around 4 million times the mass of our Sun. You cannot see the black hole directly, unless you have radio or X-ray eyes, but you see the effects. Stars orbiting a seemingly empty point at incredible speeds, and sometimes flares of high-energy radiation as material gets accelerated and swallowed. The center is ringed by a torus of gas and possibly peppered with X-ray binaries and exotic objects near the black hole. If you were to venture there, you would find space severely curved by gravity and the density of stars unbelievably high, a chaotic, energetic environment. Radiating outward from the central bulge are the spiral arms. These arms are not physical arms, like solid appendages, but rather regions of higher density that propagate through the disk, triggering star formation in their wake. As you look at the Milky Way's face, you identify the major arms. The Perseus arm is prominent, sweeping along the outer part of the galaxy. The Scutum Centaurus arm, which passes nearer the center and out. Perhaps two main symmetric arms in a grand design spiral pattern, and some spurs and feathering branches aside, like the Orion spur where the sun is. In the arms, you see blue patches and pink knots. These are hot young stars and glowing nebulae respectively. Giant molecular clouds in the arms collapse to form new stars, and those newborns, massive hot O and B stars, illuminate the surrounding clouds, H2 regions glowing pink with ionized hydrogen, and shape them with stellar winds. The blue star clusters shine strongly, but briefly before their stars die in supernovae. Indeed, scattered throughout the arms, you also see the remnants of past stellar death, supernova remnants, expanding shells of gas like the Crab Nebula or Vela, emitting tendrils of enriched material back into the interstellar medium. These events seeded heavier elements, carbon, iron, etc., into the galaxy, the very elements that later incorporated into new stars and planets, and into you and me. Between the arms and swirling around, an ethereal mist of diffuse interstellar gas persists. Dark patches in the galactic disk silhouette against the starry backdrop. These are enormous dust clouds blocking visible light. One famous such dust lane splits the Milky Way as seen from Earth, the Great Rift, caused by clouds in the inner arms. But from above, you just see them as dark swathes in the disk. If you had infrared vision, however, the dust becomes more transparent and you see even more myriad stars hidden behind. The whole galaxy rotates. The stars in the disk orbit the center in roughly the same direction. But intriguingly, the rotation curve, how orbital velocity changes with distance, is flat. Stars far out orbit just as fast as those closer in, defying the expectation if only visible matter existed. This was one key clue for the existence of dark matter, an unseen mass component enveloping galaxies. So though you do not see it, you know that the Milky Way is embedded in a vast halo of dark matter, extending well beyond the visible disk and containing perhaps 5 times more mass than all the stars and gas combined. This dark matter neither emits nor absorbs light. It interacts only gravitationally, and perhaps through some other weak forces yet unknown, but it provides the gravitational scaffold that holds the galaxy together and the cosmic web beyond. Beyond the disk and bulge, you find the stellar halo, a sparse spherical distribution of ancient stars and globular clusters. Globular clusters, as you see, are compact spheres of tens of thousands of very old stars orbiting the galaxy in all directions. They appear as glittering dense balls, mostly toward the galactic bulge, but also some far out. These are fossils of the early galaxy formation, essentially. The halo stars and clusters often have very low heavy element content, metallicity, indicating they formed before previous generations of stars had seeded the environment with heavy elements. There are about 150 known globular clusters swarming around the Milky Way, each like a beehive of stars, perhaps 12 to 13 billion years old. Their orbits take them plunging through the disk and out again, oriented randomly. Our vantage now drifts further outward, and the whole Milky Way appears smaller. You note it is a barred spiral galaxy. The central bulge has a bar structure, a stretched nucleus of stars, from whose ends the spiral arms likely emanate. Indeed, surveys of stars at the center show an elongated bar shape. Such bars are common in spiral galaxies and can drive gas inward, perhaps helping fuel star formation or feed the central black hole. The Milky Way's bar is subtle to our eyes, but distinct in infrared studies. Encircling the Milky Way is also a tenuous halo of hot gas, observed via X-ray emission, and even the remnants of past devoured galaxies, streams of stars that were torn from dwarf galaxies that ventured too close, now wrapping around the galaxy in giant loops. Now your mind's eye travels even further out, such that the entire Milky Way is seen as a small spiral among others. The night sky as we know it with constellations is but one perspective from within. From out here, those constellation patterns disappear as you see the true 3D arrangement of stars. The Milky Way appears about 100,000 light-years in diameter, with the disk perhaps only 1,000 light-years thick. It contains perhaps 200 to 400 billion stars, hard to count precisely, plus interstellar gas equal to maybe 10 to 15% of the total luminous mass, and that central black hole. Now you begin to perceive that the Milky Way is not alone. It is part of a small cluster of galaxies we call the local group. The nearest big companion is the Andromeda Galaxy, M31, a spiral slightly larger than the Milky Way, about 2.5 million light-years away. You turn your view toward it, a grand spiral with perhaps 1 trillion stars. Even from Earth, it's visible as a smudge in dark skies. From this omniscient vantage, you see its spiral arms and dust lanes clearly. It too has satellite galaxies. In fact, as you look between the Milky Way and Andromeda, you notice many small elliptical fuzzballs and irregular fragments. These are dwarf galaxies bound in the local group. The Milky Way alone has dozens of known dwarf satellites. The large and small Magellanic Clouds are the most luminous, visible as cloudy patches in the southern Earth sky, but also fainter ones like Sagittarius Dwarf, currently being tidally disrupted, Draco, Ursa Minor, Sculptor, Fornax dwarfs, and many ultra-faint dwarfs discovered in recent surveys. Andromeda has its own entourage of dwarfs. The third largest member of the local group is the Triangulum Galaxy, M33, a graceful smaller spiral orbiting perhaps around Andromeda. As gravity dictates, Andromeda and the Milky Way are actually moving toward each other. In about 4 billion years, they will begin to collide and merge, dancing a gravitational waltz that will fling stars into new orbits and trigger cascades of starbirth as gas clouds slam together. Eventually, they will likely form a single elliptical galaxy, sometimes nicknamed Milkomeda. But for now, they are distinct island universes, drifting closer in the cosmic ocean. Our local group is falling toward a larger structure, the Virgo cluster, a massive cluster of galaxies about 50 to 60 million light-years away, containing thousands of galaxies. Indeed, step back further, and you behold that galaxies collect into clusters and superclusters along filaments, with great voids in between, the cosmic web. The local group and the Virgo cluster, and others, are part of the Virgo supercluster, or local supercluster, although modern understanding defines an even larger entity called Laniakea supercluster, which includes Virgo and other clusters, all gravitationally moving together. At this truly grand scale, a few 100 million light-years across, the pattern of the universe emerges clearly, like a sponge or foam, where galaxies are concentrated along filaments and sheets surrounding vast, empty voids. It's as though the large-scale structure has a web-like or honeycomb pattern. This is the cosmic web, the result of initial tiny density fluctuations in the early universe that grew under gravity into the complex structure of clusters and voids. The nodes of the web are rich clusters of galaxies, like Virgo, connected by filaments, lines of galaxies and groups, and between them lie voids 100 million light-years across with very few galaxies. One might wonder, why this filamentary structure? Cosmological simulations and observations tell us it's due largely to dark matter scaffolding. Dark matter clumped first, forming a web-like structure under gravity, with voids where there was slightly less matter initially. Normal matter fell into those gravitational wells, forming gas clouds that became galaxies at the nodes and along filaments. Over billions of years, gravity steadily draws matter into this web, making clusters grow by accreting smaller groups and the filaments draining into clusters. Our local group is on an outskirt of the Virgo cluster, likely slowly being pulled toward it. At these scales, you also become aware of the mysterious presence of dark energy, an even more enigmatic component of the universe. About 70% of the total energy content of the universe appears to be in this form. It does not cluster like matter. It is uniform, permeating all of space, causing space itself to expand at an accelerating rate. Whereas gravity, from matter, works to slow expansion and pull things together, dark energy pushes space to expand faster. About 6 billion years ago, dark energy's effect became dominant over matter's self-gravity, and since then the expansion of the universe has been speeding up. Thus, while a localized cluster like Virgo can overcome expansion due to its own gravity binding it, distant clusters are receding from each other at ever-increasing speeds. Now, imagine time as well. You look far enough out in space. You also look back in time, because light takes time to reach you. So at the largest scales, you can see glimpses of the early universe. For example, the cosmic microwave background, CMB radiation, the afterglow of the Big Bang, comes from all directions. From a time about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and became transparent. It's a faint glow primarily in microwaves now, due to the redshift from the expansion, but it shows tiny temperature fluctuations, the seeds of the future galaxies and clusters. That is the ultimate horizon of the observable universe for electromagnetic waves. Beyond that, the universe was opaque plasma, but neutrinos or gravitational waves can give hints from even earlier. Your journey of the mind now spans 13.8 billion years of history and tens of billions of light years of space. You witness how from a nearly uniform hot plasma, the cosmos expanded and cooled, forming hydrogen and helium gas, which coalesced into the first stars and galaxies a few 100 million years later. Those first stars, population 3 stars, were massive and short-lived, exploding as supernovae that enriched the cosmos with heavier elements. Galaxies formed and merged and grew. In the centers of many, massive black holes formed early and grew by accreting matter, sometimes shining as quasars that outshone entire galaxies with their brilliance. You could see in extremely distant galaxies, thus, early in time, these quasars and proto-galaxies flickering in the cosmic dawn. Over billions of years, galaxies matured into the shapes we see today. Some became ellipticals, often from mergers of spirals. Others remained spirals. Dwarf galaxies aplenty swarmed around bigger ones or drifted lonely in voids. Clusters assembled. Bubble-like voids grew as matter flowed into structures. Now consider that all the while, through the vastness of space and time, the atoms that now make up your body were forged in this cosmic process. The hydrogen in your cells likely formed minutes after the Big Bang. The carbon, oxygen, nitrogen in your body were synthesized in the core of a star that lived and died before our sun was born. The iron in your blood, the calcium in your bones, those came from the violent explosion of a supernova scattering its enriched guts into space. That dust and gas then coalesced 4.6 billion years ago in a swirling disk around the young sun to form Earth and all life's ingredients. The water you drink likely contains hydrogen from the beginning of time and oxygen from long-dead stars, combined on Earth perhaps by chemical processes involving those same elements. Eventually, perhaps inevitably, from this mix of elements on Earth, life emerged, and eventually that life evolved to conscious beings able to ponder their origins. We are such stuff as the stars made, literally stardust brought to life. The space out there is not just black void. It is the matrix from which everything came. From this grand perspective, slowly you make your way back home. Zooming in from intergalactic space, you find the local group, the Milky Way, one of its spiral arms, the Sun, and our pale blue Earth circling it. You see Earth anew, a bright blue oasis amid the darkness, its white clouds swirling in an active dance, its polar caps gleaming, its green-brown continents showing hints of forests and deserts. Sliding down through Earth's comforting atmosphere, you return to where you began, sunlight warming human skin, wind rustling through leaves. Perhaps it's sunrise now. The sun peeks over the horizon, lighting dewdrops on grass into tiny rainbow sparkles. You feel the gentle warmth again on your face. Only now you carry the awareness that this warmth has an ancient, epic journey. From the core of our star where it was born, across the vacuum of space, touching worlds on the way, reflecting off moon and rings, until finally it caressed your cheek. You open your eyes. Above, the morning sky is blue and quiet. The same sun whose fires we skimmed now lights up the clouds in shades of pink and gold. The same earth where life flourishes now lies beneath your feet, solid and nurturing. You realize something profound. The line between us and space is an illusion of perspective. The air you breathe was assembled from atoms gathered across the galaxy. The heat in your body is the stored energy of the sun's rays, captured by plants and passed as food to you. The calcium in your bones was forged in a star's supernova ash. The very concepts of today and yesterday make no sense without the cosmic cycles of Earth's rotation and orbit. You are not separate from the universe. You are a part of its exquisite, ongoing story. In this moment of stillness, standing on Earth under the sun's glow, you can feel the unity of it all. The solidity of the ground, the cool whisper of the breeze, the distant glitter of stars that will appear by evening. It's all connected. The space that seems so remote is in fact within you, around you, of you. We look up on a clear night and see thousands of tiny lights sprinkled across the sky. From ancient times to the present, people have been captivated by the stars. They have inspired wonder, guided travelers, and sparked countless myths and legends. Humans imagined patterns in them and told stories about gods, heroes, and animals in the heavens. We use the stars to navigate oceans and to mark the seasons. But what are these brilliant pinpricks of light really? Stars are giant, luminous balls of plasma, held together by their own gravity and powered by nuclear fusion at their cores. In simple terms, a star is a colossal nuclear furnace in space, constantly fusing lighter elements into heavier ones and releasing tremendous energy as light and heat. They seem eternal and unchanging to us, but in reality, stars are born, they age, and they die, undergoing dramatic changes over millions or billions of years. Our sun is one such star. In fact, it's the only star close enough for us to feel its warmth and light directly. And it's just one among an uncountable multitude of stars in the universe, each with its own story. Now, imagine journeying into a vast cosmic cloud far out in space, where new stars are born. These regions are called nebulae, enormous, diffuse nurseries of gas and dust, sprinkled throughout the galaxies. They are the cradles of star formation. If you could float inside one, you might see faint, ghostly glows and dark, opaque patches where starlight from outside is blocked. The famous pillars of creation. Photograph of the Eagle Nebula, for instance, shows towering columns of gas and dust rising like mountainous spires. Within those cold, shadowy pillars, new stars are slowly taking shape. The Great Orion Nebula, visible as a faint smudge in Orion's sword, is one such stellar nursery, a cavern of gas and dust over 20 light-years wide, where thousands of baby stars are forming. Here, in the cold, dark depths of a nebula, the story of a star begins. A slight nudge, perhaps the shockwave from a distant supernova or a random density fluctuation, causes parts of the cloud to begin collapsing under their own gravity. Over thousands to millions of years, a portion of the nebula's gas gathers more and more mass, pulling in surrounding material. As this pocket of gas shrinks, it grows denser and hotter, and it starts to spin faster. Eventually, it forms a growing ball of gas known as a protostar, a baby star that's still gathering mass. Surrounding it, a flat disk of gas and dust often forms, whirling around the protostar. Protostars also often fire out bipolar jets, narrow beams of gas blasting out from their north and south poles. These high-speed jets can plow through the surrounding nebula, creating glowing shockwaves and carving cavities in the cloud. The protostar at the center continues to contract and heat up as gravity relentlessly squeezes it. Deep in the core of this protostar, temperatures climb into the millions of degrees. The gas is mostly hydrogen, the simplest and lightest element. When the core temperature reaches roughly 15 million degrees Celsius, something miraculous happens: ignition. Hydrogen nuclei begin to fuse together to form helium, unleashing a tremendous amount of energy. This is the moment a star is truly born. The protostar has become a full-fledged star, blazing with its own light. The once dark core suddenly glows brilliantly, and the outward pressure of this new energy release halts the gas collapse. The infant star turns on, so to speak, and starts shining. The surrounding cocoon of leftover gas and dust gets blown away by the fierce stellar winds and radiation now pouring from the newborn star. The star stabilizes, no longer contracting, as a balance is struck. It has entered the long, stable phase of its life, known as the main sequence. Often, stars do not form alone. Many newborn stars come in groups called star clusters. Our Sun likely formed in a cluster with several sibling stars, which have since drifted away. Once nuclear fusion starts in the core, a star finds an equilibrium. Outward pressure from the fusion energy balances the inward pull of gravity, and the star stops shrinking. It becomes stable, neither collapsing nor exploding, steadily glowing. The star will remain in this state, fusing hydrogen in its core, for the vast majority of its lifetime. It's as if the stellar engine is idling at a steady rate. This newfound stability allows the star to shine consistently for a very long time. Millions, even billions of years will pass with the star in this tranquil main sequence phase. Our Sun is in fact in this phase right now, and has been for about 4.6 billion years. This stability is fortunate for us. It means the Sun's energy has been steady enough to allow life to develop on Earth, and will continue for eons more. If our Sun were a short-lived massive star, life as we know it might never have had the chance to arise in the brief stellar lifetime. Main, sequence stars like the Sun quietly convert hydrogen to helium, radiating energy into space and providing warmth and light to any orbiting planets. In this main sequence stage, a star shines by nuclear fusion, fusing hydrogen atoms into helium in its core, and in doing so, it releases an absolutely colossal amount of energy. To give a sense of scale, our Sun fuses about 600 million tons of hydrogen every second, turning it into about 596 million tons of helium. The missing mass, roughly 4 million tons per second, is converted to pure energy according to Einstein's famous equation E=mc2. 4 million tons of matter turned into energy every single second. This energy then radiates outward from the core, through the Sun's layers, and eventually into space as heat and light. The numbers are mind-boggling. The Sun's energy output each second is about 3.8 × 10⁻²⁶ watts, a figure almost impossible to imagine. To put it in human terms, the power the Sun releases every second is equivalent to the energy from billions of nuclear bombs exploding at once. Yet this gargantuan output has been running continuously for billions of years, and will continue for billions more. It's sobering to realize that for most of human history, the source of the Sun's power was a mystery. Only in the 20th century did scientists like Arthur Eddington and Hans Bethe figure out that nuclear fusion is what makes the stars shine. Millions of such stars fill our galaxy, each a massive energy source blazing in space. Not all stars are like our Sun, however. Stars come in a stunning variety of sizes, colors, and luminosities. Some are far bigger and hotter than the Sun, shining blue, white, and piercingly bright. Others are smaller and cooler, glowing a faint red. The color of a star is a clue to its surface temperature. Hotter stars emit more blue, white light. Cooler stars more red, orange light. For example, in the constellation Orion, you can spot a contrast between the supergiant star Betelgeuse, which shines with a reddish hue, and Rigel, which gleams bluish-white. In general, a blue star might be tens of thousands of degrees at its surface, while a red star might be only a few thousand degrees. These differences correspond to spectral classes. Another example: the star Sirius, the brightest star in Earth's night sky, is about twice the Sun's mass and has a surface temperature of around 9,400 K, giving it a white-blue sparkle. On the other hand, our Sun is yellow, white, and a typical small red dwarf star would look deep red to our eyes. The vast majority of stars in our galaxy are actually small, cool red dwarfs. Perhaps 70–80% of all stars fall into this category. These red dwarfs are so dim that not a single one is visible without a telescope. In fact, the smallest true star ever measured is only slightly larger than the planet Saturn. With just about 8% of the Sun's mass, it barely manages to sustain fusion. Were it any smaller, it would fail to ignite and become a failed star, known as a brown dwarf. By contrast, most of the stars we see sparkling in the night sky are the larger, more luminous types that, while much rarer, shine hundreds or thousands of times brighter than red dwarfs and can be seen across great distances. If you stood on a hypothetical planet orbiting a red dwarf, the star might hang in a dim red sky, casting an eerie dusk, like light even at noon. By contrast, a planet around a hot blue-white star would be flooded with a stark, bluish illumination and intense ultraviolet rays. Size and mass have a profound effect on a star's fate. In general, the more massive a star, the hotter and brighter it burns, and the shorter its life. A star 10 times more massive than the Sun might emit thousands of times more energy, blazing a brilliant blue, white, but it will use up its fuel at an unsustainable rate. It's the difference between a gas, guzzling sports car and an economy car. The massive star burns through its fuel quickly, while a small star is extremely fuel efficient. Massive stars live fast and die young in a cosmic sense. Such a star might last only a few million years before it exhausts its core fuel. In contrast, a tiny red dwarf sips its hydrogen fuel so slowly that it can continue burning for hundreds of billions or even trillions of years. To put it in perspective, the universe itself is about 13.8 billion years old, so no red dwarf has had time to even come close to dying yet. Our Sun lies somewhere in the middle of the mass range. It's a G-type yellow dwarf, not exceptionally massive or small. It will have a total lifetime of roughly 10 billion years, moderately long by stellar standards. So far, the Sun has been shining for about 4.6 billion years, and it has about 5 billion to go before it starts to run out of core hydrogen. Because of these lifespan differences, no red dwarf star has ever died in the history of the universe. The universe simply hasn't been around long enough for the smallest, slowest, burning stars to use up their fuel. Even the oldest red dwarfs, born shortly after the Big Bang, are still shining today and will keep on shining for trillions of years to come. By the far distant future, long after bigger stars like the Sun have died, red dwarfs will be the last stars remaining, quietly glowing red in a fading universe. On the other end of the spectrum, many massive stars have lived and died in that same time, blazing through their fuel in a few million years and ending in catastrophic explosions. In a sense, the cosmos has a way of favoring the slow and steady when it comes to longevity. Eventually, even the most long-lived star will run low on fuel. When a star has fused most of the hydrogen in its core into helium, it starts to leave the stable phase of its life. The delicate balance that maintained the star for so long begins to falter. With less nuclear energy being produced in the core, the outward pressure that held the star up drops. The core, now largely helium, begins to contract under gravity since nothing is pushing back as strongly. And when the core of the star contracts, surprising things happen in the layers around it. The contracting core heats up a lot. This intense heat radiates into the surrounding shell of hydrogen that wasn't previously hot enough to fuse. Now that shell of hydrogen does begin fusion. So hydrogen fusion essentially migrates from the core to a shell around the core. Meanwhile, the helium core will eventually get hot enough to ignite a new kind of fusion. It will start fusing helium into carbon. The star's internal structure rearranges: a small, dense, very hot core fusing helium, and a shell around it fusing hydrogen. All this generates a tremendous amount of energy in the star's interior. The result is that the outer layers of the star are pushed outward, far outward. The star balloons in size. As the surface expands, it cools. The once yellow-white star becomes a cooler red star. It has now become a red giant. The term is literal. It is redder in color and gigantic in size compared to before. A star in this phase can swell to tens or even hundreds of times its original diameter. One day, about 5 or 6 billion years from now, our sun will undergo this transformation into a red giant phase. As it approaches old age, it will exhaust the hydrogen in its core and begin fusing helium. The sun's core will contract and heat up, and its outer layers will expand dramatically. In the process, the sun's radius will likely grow so large that it engulfs Mercury and Venus, the two innermost planets, and comes perilously close to Earth's orbit. From Earth's perspective, the sun would swell to an enormous red orb dominating the sky. The temperature on our planet would skyrocket. In fact, long before the sun's surface actually reaches Earth, the intense heat will boil away Earth's oceans and atmosphere and render our planet uninhabitable. Essentially, a scorched, lifeless rock. There is a chance Earth might be swallowed up entirely by the sun's expanded atmosphere, or it might just survive, parched and baked. Either way, the inner solar system will be unrecognizable. The sun will not only grow in size, it will also lose a lot of its mass via a powerful stellar wind. With less mass, the sun's gravitational pull on the remaining planets will weaken, causing those planets to drift outward to wider orbits. This red giant phase is a dramatic change, but fortunately for us, it's billions of years away in the future. For a star of the sun's mass, this red giant stage is essentially the beginning of the end. After perhaps 1 billion years in the red giant phase, the sun's core will have fused its helium into carbon and oxygen. It won't be hot enough to fuse those heavier elements, so the core will remain as a hot ball of carbon and oxygen. Without new fusion to support it, the core will contract further, and the outer layers of the sun, which expanded so far out, will become increasingly unstable. In a series of pulses, those outer layers will be expelled into space, creating a brilliant cloud of gas around the dying star. This glowing shell of ejected gas is called a planetary nebula. The sun, in its death throes, will thus cast off its atmosphere, which will drift away as an expanding bubble of gas. Planetary nebulae can be stunningly beautiful. Observed through telescopes, they appear as multicolored rings or shapes of glowing gas. In a few tens of thousands of years, the sun's shed gases will mix into the interstellar medium, enriching it with elements the sun made. All that remains of the sun at this point will be its former core. This exposed core is a hot, extremely dense orb about the size of Earth. It's called a white dwarf, the final state of a low to mid-mass star like our sun. A white dwarf no longer has fusion happening in its center. It is supported against further collapse by quantum pressure. It is, essentially, a stellar ember, an extremely hot cinder left over from the star's life. When it first forms, a white dwarf is incredibly hot and glowing white, blue, but it's also very small, so its total light is relatively faint. Over billions of years, it will cool and fade. To appreciate just how dense a white dwarf is, it packs roughly the mass of the Sun into a volume the size of Earth. Imagine compressing something as massive as a star into a ball only 8,000 miles across. The density of such an object is mind-boggling, on average about 1,000,000 times denser than water, meaning a single cubic centimeter of white dwarf material would weigh on the order of 1 ton. In other words, a teaspoon of white dwarf matter would weigh several tons here on Earth. The gravity on its surface would be hundreds of thousands of times stronger than Earth's. If you somehow stood on a white dwarf, you would feel yourself weighing so much that you'd be crushed instantly. Over a very, very long time, a white dwarf will radiate away its heat and cool down. Eventually, after many tens or hundreds of billions of years, it would become a black dwarf, essentially a cold, dark, stellar remnant. In the case of our Sun, this is its ultimate fate, to spend eternity as a faint, white, hot star gradually cooling into darkness. Indeed, most stars end their lives quietly as white dwarfs, simply cooling and fading away. Only the most massive stars end in the spectacular supernova route. Now consider a star much more massive than the Sun, say a star born with 10 or 20 times the Sun's mass, or even more. These stars go through their lives much more quickly and violently. They too will leave the main sequence once their core hydrogen is exhausted, but the sequence of events is even more extreme. Such a star becomes a red supergiant instead of a mere giant. One of the best known examples of a red supergiant is Betelgeuse, the bright reddish star in Orion's shoulder. Betelgeuse is about 15,020 times as massive as the Sun and has expanded to a tremendous size. Observations estimate it is on the order of 700–800 times the Sun's radius. If Betelgeuse were placed at the center of our solar system, it would extend well past the orbit of Mars and possibly even approach Jupiter's orbit. It's so large that its volume would encompass tens of millions of suns. And Betelgeuse isn't even the largest star known. A few rare hypergiant stars, such as UY Scuti or Stephenson 218, are believed to have radii around 1,500 × 2,000 times that of the Sun. Truly monstrous stars. These colossal stars are extremely luminous and short-lived. Betelgeuse, for instance, is only on the order of 10 million years old, yet it is already in its dying phase. In fact, Betelgeuse is expected to explode as a supernova in the relatively near future. It could happen anytime in the next 100,000 years, which is a blink of an eye for a star. It might be tomorrow, or it might be far beyond our lifetimes. We can't pinpoint exactly when, but we know the star is nearing the end of its life. When Betelgeuse does explode, it will likely shine as bright as the full moon in our sky for a few weeks and be easily visible even in daytime. What leads a star like Betelgeuse, or any other massive star, to such a violent end? The difference lies in what happens in the star's core after the hydrogen is used up. A high-mass star has the gravity and pressure to push the boundaries of fusion much further than a star like the Sun can. When hydrogen in the core runs out and the core contracts, the temperature soars high enough to ignite the fusion of helium into carbon and oxygen. Once helium in the core is exhausted, the core contracts and heats again, and the star's envelope expands into a red supergiant. But in these behemoths, the core gets hot enough to start fusing carbon into heavier elements. The pattern continues in a kind of fusion cascade. Carbon fuses into neon, magnesium, and sodium. When carbon is depleted, the core contracts and heats, and then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. And finally, Silicon fuses into iron and nickel. The star builds up onion like layers of fusion shells. Hydrogen burning in an outer shell, helium burning in a shell beneath that, carbon burning in a shell closer in, and so forth, all the way to a growing iron core in the center. The iron core is the final product of fusion, because fusion of iron doesn't release energy, it consumes energy. That's a crucial point. Up until iron, fusion can power the star, but once the core accumulates iron, further fusion would not yield net energy. So, as iron builds up in the core of a massive star, the star is living on borrowed time. The star continues burning elements in shells around the core, piling more and more iron into the center. Meanwhile, the time spent on each successive fuel is shorter and shorter. A massive star might spend millions of years fusing hydrogen, maybe 1 million years fusing helium, but perhaps only a few years fusing carbon, a few months fusing oxygen, and mere days fusing silicon into iron. Eventually, the iron core reaches a critical mass. At that moment, the star can no longer support its own weight. For a massive star, this is the final act, and it's dramatic. When the iron core can no longer hold itself up, it collapses catastrophically under gravity. This collapse happens incredibly fast. In under a second, the core implodes. The temperatures in the core skyrocket, and atomic nuclei get crushed together. Protons and electrons merge into neutrons, so the core essentially becomes one giant atomic nucleus, a ball of neutrons. The collapse is suddenly halted by the degeneracy pressure of neutrons. In that instant, the infalling material rebounds off the stiff neutron core. A powerful shockwave is sent roaring outward through the star's interior. The core collapse and rebound is so intense that it unleashes an enormous burst of neutrinos and a tsunami of energy. The star's outer layers are blown off in one of the most violent events in the universe, a supernova explosion. If the core of the star at the time of collapse is below about 2003 solar masses, it will become a neutron star, the ultra-dense, city-sized stellar remnant composed almost entirely of neutrons. If the core is above that mass threshold, even the neutrons cannot halt the collapse, and the core will continue collapsing into a black hole, a point of practically infinite density. Either way, the core's collapse triggers the supernova blast. In a supernova, the star's entire outer structure is ripped apart. The star's brightness increases tremendously for a short time. A supernova can briefly outshine an entire galaxy of normal stars. Imagine a single star suddenly shining brighter than 100 billion stars combined. That is what a supernova can do. It will radiate as much energy in a few weeks as the sun will in its entire 10 billion year lifetime. If such an event happens relatively nearby, it can be visible from Earth, even in the daytime. Human astronomers have indeed witnessed supernovas in the past. Historical records from East Asia and the Middle East describe guest stars appearing in the sky. For example, in 1054 AD, Chinese astronomers noted a new star that was visible in daylight for weeks. This was a supernova. Another supernova was observed in 1604. More recently, in 1987, a star exploded in the Large Magellanic Cloud and could be seen by the naked eye. In our own Milky Way, no supernova has been observed in the past 4 centuries, but statistically, we expect a few per century meaning we could be due for another any time in the future. In the chaotic violence of a supernova, there is a remarkable silver lining. This is the event that forges many of the heavy elements that enrich the universe. During the star's normal life, it created elements like carbon, oxygen, and silicon in its core. But elements heavier than iron, such as gold, platinum, and uranium, require the extreme conditions of a supernova to form. In the supernova blast, atomic nuclei slam together in rapid fire reactions, building up many of the heaviest elements on the periodic table. The explosion then scatters these newly forged elements out into space. The stellar ashes, Carbon, oxygen, calcium, iron, gold, and so on are flung far and wide, mixing into the gas between stars. Supernovae are therefore cosmic gardeners, seeding the interstellar medium with the ingredients for future generations of stars and planets. The very material that makes up our Earth and our bodies has gone through this cycle. The iron in your blood, the calcium in your bones, the oxygen that you breathe, those atoms were once created in the interior of a star or in a supernova explosion. As a NASA astrophysics team put it, we truly are made of stardust. The calcium in your teeth, the iron in your hemoglobin, the carbon in your DNA, all were forged in stellar furnaces. Indeed, without the carbon, oxygen, nitrogen, and other elements spread by stars, Earth could not have solid ground, air, or water, and life as we know it would be impossible. We owe our existence to stars that died long before the Earth formed. Indeed, without the heavy elements from stars, there would be no rocky planets, no air or oceans, and no living beings. Meanwhile, what's left of the star's core becomes either a neutron star or a black hole, as mentioned. Neutron stars are fantastical objects. Imagine something more massive than our Sun crushed into a sphere only about 20 kilometers across. They are so dense that a single teaspoon of neutron star material would weigh around 1 billion tons on Earth. The gravity on its surface is so strong that if you dropped an object from 1 meter above, it would hit the surface in a microsecond, accelerating to millions of kilometers per hour. Neutron stars often spin rapidly. Some rotate multiple times per second and emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep around like lighthouse beams. If such a beam points toward Earth periodically, we see pulses of radiation. These are observed as pulsars. The first pulsar was discovered in 1967 as a mysterious radio pulse every 1.3 seconds, so regular that the discoverers jokingly nicknamed it LGM-1. Half, seriously wondering if it was a signal from an alien civilization. We now know it was a rapidly spinning neutron star. Pulsars can spin unbelievably fast. The fastest known pulsar rotates more than 700 times per second. Imagine an object more massive than the Sun, spinning hundreds of times a second. It defies the imagination. Some neutron stars, called magnetars, have magnetic fields even more extreme, up to 1,000 times stronger than a typical pulsar. A magnetar's field is so extraordinarily powerful that, at a few thousand kilometers away, it could disrupt electronics on Earth. Occasionally, magnetars undergo starquakes that release giant flares of X-rays and gamma rays. If the star's remnant core was too massive to form a stable neutron star, it continues collapsing beyond even the neutron stage. In that case, the core becomes a black hole, an object with gravity so intense that nothing, not even light, can escape from its vicinity. A black hole formed from a single star might contain, say, 5 or 10 solar masses of material, but all of that mass is crushed down into an infinitesimally small volume at the center. The region around it from which not even light can escape is called the event horizon, effectively the point of no return. For a black hole with the mass of our Sun, the event horizon would be only about 3 kilometers in radius. If the Sun was somehow compressed into a sphere only 6 kilometers across, it would become a black hole. For something as massive as Earth, the event horizon would be barely a centimeter across, meaning Earth would have to be crushed to the size of a marble to turn into a black hole. These numbers illustrate how incredibly dense and compact black holes are, matter and gravity in their most extreme state. Because no light comes from a black hole itself, we cannot see a black hole directly as a glowing object. A lone black hole floating in space would appear truly black, a gravitational trapdoor in the cosmos. However, we can detect black holes by their effects on surrounding matter. Often, a black hole will have gas around it. That gas forms a swirling accretion disk as it spirals into the black hole, and it gets extremely hot, often emitting X-rays that telescopes can detect. We also observe stars orbiting an invisible mass. For example, the center of our Milky Way galaxy has stars whipping around an unseen object, which we know is a supermassive black hole. In recent years, astronomers have even managed to capture direct evidence of black holes by imaging their silhouettes. In 2019, the Event Horizon Telescope project released the first picture of a black hole, or rather, of the glowing gas around a black hole's event horizon. It showed a ring of light and a dark central shadow, exactly as predicted by physics. This was the supermassive black hole in a distant galaxy. And in 2022, we finally saw a similar image of the supermassive black hole at our own galaxy's center. Black holes, once purely theoretical, are now actively studied cosmic phenomena. Amazingly, even after a star has died, its story might not be completely over. Sometimes, the remnants left behind can have dramatic afterlives. For example, if two neutron stars eventually orbit each other, they will gradually spiral inward over time. After millions of years, they may collide in a spectacular event called a kilonova, a merger explosion even more energetic than a typical supernova. Such mergers produce strong bursts of gravitational waves that propagate outward. In 2017, scientists detected gravitational waves from a neutron star collision and also saw a flash of light from it. This was the first time we observed both gravitational waves and electromagnetic radiation from the same event. That neutron star merger forged copious amounts of heavy elements and scattered them into space. Black holes can merge with each other too. When they do, they emit a flood of gravitational waves. We can't see the merger, but detectors on Earth can hear the fabric of space tremble. In 2015, LIGO observed such signals for the first time, confirming a major prediction of Einstein's theories. These phenomena show that even in death, stars can continue to influence their surroundings in extraordinary ways. After a supernova fades, all that remains of the star may be a dense remnant, plus an expanding cloud of gas and dust, the supernova remnant. The ejected material from the star, now racing outward, sweeps up the surrounding interstellar gas and dust, creating a shell or complex filamentary structure that can glow for tens of thousands of years. The Crab Nebula, for instance, is the beautiful filamented remnant of the supernova of 1054 AD, still expanding at thousands of kilometers per second. Over time, these remnants disperse and mix with the interstellar medium. And here, the grand cycle turns anew. The scatterings of old stars eventually become part of new nebulae, providing the enriched raw material for future stars. The next generation of stars will form out of clouds, seeded with the heavy elements of previous generations. Our Sun is thought to be a late generation star, born roughly 4.6 billion years ago from a nebula already seeded with heavy elements by earlier supernovae. Those elements made it into our Earth and into us. We truly are, as the saying goes, children of the stars. Stars, then, are not only beacons of light, but cosmic alchemists and recyclers. Through their life cycles, they transform the primordial hydrogen and helium into a rich array of heavier elements. And through their deaths, they redistribute those elements across space to fertilize new star formation. Generations of stars have built up the carbon in our tissues, the oxygen in the air, the silicon in rocks, and every atom of every element heavier than helium. The universe began with mostly hydrogen and helium, and it is the stars that fashioned all the rest inside their hot cores. It's a magnificent ongoing circle of stellar evolution and renewal, star birth, star life, star death, and new stars born from the remnants. This cycle has been going on for billions of years and will continue for billions more. It is the engine that drives the chemical enrichment and dynamic evolution of galaxies. When we survey the night sky filled with stars, we are gazing at a vast cosmic ecosystem in action. Each pinpoint of light has its own history and future. Some of those stars may be like our Sun, gently burning for eons. Others might be giant stars soon to explode, or faint red dwarfs just chugging along. There are hundreds of billions of stars in the Milky Way galaxy alone, and beyond that, billions of other galaxies each with their own billions of stars. The total number of stars in the observable universe is estimated to be around 10 to the 22. That's a 1 with 22 zeros after it. This number is so huge that it defies true comprehension. One popular comparison is that there are more stars in the universe than grains of sand on all the beaches on Earth. In fact, astronomers estimate there are on the order of 10,000 stars for every grain of sand on Earth. It's an astonishing thought. Next time you're at the beach, pick up a handful of sand and consider that the stars outnumber those tiny grains. Every one of those stars is a sun, and many of those suns have their own families of planets. The universe is teeming with stars beyond counting. Understanding the life cycle of stars gives us a profoundly richer appreciation of the night sky. When you next gaze up at the stars, remember that those twinkling lights are not mere points. They are distant suns, each with a life story spanning eons. The star that looks like a pinprick could be a giant blazing at millions of degrees, or a diminutive red ember glowing softly. Some of the stars you see tonight might already have exploded in the far past, their light only now arriving at Earth after traveling for centuries through space. In a very literal sense, we are connected to these stars. Our planet and our bodies are composed of star-born atoms. Indeed, without the heavy elements forged in stars, Earth wouldn't exist as a rocky world, and human beings could not have come to be. As the late astronomer Carl Sagan famously said, "We are made of star stuff." We are the universe's way of knowing itself, formed from the ashes of long dead stars. In the end, the saga of stars is the saga of the universe. It's a story of creation and transformation on an epic scale, of diffuse gas gathering to ignite nuclear fire, of shining stability and convulsive death, of elements forged in celestial furnaces and cast into the darkness to become the seeds of new worlds. Stars have illuminated the cosmos for over 13 billion years, and they will continue to do so long into the future. Every twinkling star in the sky is a testament to the ongoing cycle of cosmic birth and rebirth. So the next time you find yourself under a starry night, take a moment to ponder the incredible processes happening above you. Those stars are distant suns, forging the stuff of life, exploding and renewing the galaxy. They light up the darkness and spark our imaginations. Theirs is a never-ending story, one of fire and dust, life and death, and renewal. An endless cosmic dance that has shaped our universe and, ultimately, made our own existence possible. And as long as you can see the stars shining overhead, you are witnessing a part of that grand story unfolding, a story that connects us all to the cosmos and to the dazzling stars that fill the sky. The final glow of the previous story fades, but our journey among the stars is far from over. In fact, it's only just beginning. Out in the cosmic dark, countless stars still beckon with new mysteries and deeper roles to explore. We have gazed upon the life cycles of stars, their births in nebulous cradles and their deaths in explosive finales. Yet there is even more to the stellar saga. Now, let us venture further into the galactic tapestry to uncover how stars themselves shape the grand story of the universe. As we continue, imagine drifting back in time to an era before even the first star ignited. In that primordial darkness, over 13 billion years ago, the universe waited for its first light. When the first generation of stars were finally born, They were unlike any that exist today. These population 3 stars, as astronomers call them, were forged from only the simplest elements, the sole ingredients created by the Big Bang. Theory paints them as cosmic titans, perhaps 30 to 300 times the mass of our Sun, and millions of times brighter. Such massive stars would burn their fuel ferociously fast, blazing only a few million years before dying in titanic supernova explosions. Yet in their brief lives, they performed a vital service. Their searing ultraviolet light rayonized the universe's hydrogen, ending the cosmic dark ages nearly 1 billion years after the Big Bang. In those first brilliant sparks, the universe transitioned from dark and opaque to radiant and transparent, a fundamental turning point in cosmic history. When those primordial stars lived and died, they also created something entirely new: heavy elements. In their hot cores, nuclear fusion began forging elements heavier than helium, carbon, oxygen, silicon, and more. And when the first stars perished as supernovae, they seeded the cosmos with these heavier elements. Before stars, the universe lacked the ingredients for planets or life. After the first stars, space was enriched with the star stuff from which future generations could build. It's awe-inspiring to realize that nearly all the elements in our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe, were forged in the hearts of stars that lived long ago. Those early explosions scattered the raw materials for new stars, new planets, and eventually us. Little wonder that astronomer Carl Sagan's poetic truth resonates. We are made of star stuff. The universe had to go through the fires of stellar furnaces to fill the periodic table beyond hydrogen and helium. With each generation of stars enriching the cosmic brew, subsequent stars were born with higher metallicity. Thus began an ongoing chemical evolution, each stellar generation shaping the composition of the next, gradually building up the complexity needed for rocky worlds and living beings. In the wake of the first stars, new generations of stars began to form from the ashes. Astronomers classify these stellar populations by their metal content. The ancient stars that followed the primordial ones are dubbed Population 2. They contain only a small trace of heavy elements, just a smattering inherited from those first supernovae. Many Population 2 stars still shine today. They are the oldest stars in galaxies, often found in the halos of galaxies or in ancient globular clusters. In fact, some globular star clusters in our Milky Way are nearly 13 billion years old, almost as old as the universe itself, and their stars preserve a fossil record of the early cosmos. These venerable suns are cosmic time capsules, their faint metal content telling us they formed when the universe was still poor in heavy elements. By contrast, Population Y stars, like our own Sun, are rich in heavier elements. Population I stars are younger, born later in cosmic history, from gas already recycled and enriched by countless prior stellar lives. They reside mostly in galactic disks and include many bright, hot stars, as well as middle-aged stars like the Sun. The distinction between these populations isn't just academic. It's central to understanding how galaxies formed and evolved. In the Milky Way, for example, the spherical halo of old Population 2 stars may be remnants of the galaxy's original build and early mergers, whereas the disk's Population 1 stars reflect ongoing star formation fueled by interstellar gas. The very structure of our galaxy, a thin disk with spiral arms, a central bulge, and a diffuse halo, has been shaped by the continuous birth and death of stars over billions of years. Early in our galaxy's youth, it likely underwent titanic mergers with smaller protogalaxies. One dramatic merger, revealed by the European Gaia spacecraft's star mapping data, occurred around 10 billion years ago when the Milky Way swallowed a dwarf galaxy, now nicknamed Gaia Enceladus, or the Gaia Sausage. This cosmic collision delivered a vast influx of stars into the Milky Way's halo. The evidence is written in the motions and chemical makeup of many halo stars, which are distinct from native Milky Way stars, a sign that they originated in another galaxy. During such mergers, bursts of star formation likely ignited as gas clouds were jolted and compressed. Thus, the Milky Way's early history, the thickening of its disk, the build-up of its stellar halo, was driven in part by starbirth sparked in the chaos of mergers. Time and again, galaxies grew by merging and forming new stars, with each generation of stars influencing the galaxy's structure and dynamics. Star formation itself tends to be a self-limiting and self-propagating process. Massive young stars radiate intense light and spew stellar winds, which can carve cavities in the surrounding gas. When the most massive of these stars go supernova, they blast the gas with shockwaves. This feedback can either trigger new stars or quench star formation. In dwarf galaxies, a few vigorous supernovae can blow out much of the gas, stifling further starbirth. In larger galaxies, star formation and supernova feedback regulate each other in a complex dance, ensuring that galaxies don't convert all their gas into stars at once. Indeed, observations show that the universe's star formation rate peaked about 10 to 11 billion years ago and has been declining ever since. At its height, galaxies were forming stars at a frenetic pace, so much so that today's rate is only a few % of that peak. Over billions of years, much of the free gas in galaxies has been used up or locked into stars, and energetic feedback from stars has kept a lot of remaining gas too hot to collapse easily. Our cosmos is slowly simmering down. Still, new stars continue to be born even now, especially in the rich spiral arms of galaxies. In our Milky Way, stellar nurseries like the Orion Nebula are actively turning out fresh stars. But the overall trend is inexorable. The fuel for star formation is finite, and eventually it will run low. Gazing far into the future, astronomers estimate that in roughly 100 trillion years, all the usable star-forming gas will be exhausted or locked up. By that far epoch, the era of star formation will draw to a close. The universe will transition into a quieter stage, dominated by the embers of stellar evolution. Myriad white dwarfs slowly cooling into black dwarfs, neutron stars and black holes lurking in the darkness, and only the occasional new star flickering to life from the rare merger of two old stellar remnants. But fear not. At present, the universe is still richly populated with shining stars, and we live in a cosmos that is very much alive with stellar light. Let's turn our attention to the stars as architects of their galaxies. Every galaxy's visible beauty, its shimmering starlight, its glowing nebulae, comes from stars. Stars delineate the spiral arms of disk galaxies, with luminous young star clusters tracing out spiral patterns like celestial fairground lights. In majestic barred spirals and elegant ellipticals alike, the collective light of billions of stars gives each galaxy its form and color. Hot, young stars glow blue, white, giving star-forming galaxies a bluish hue, while older, cooler populations lend a yellow-red warmth to galaxy bulges and ellipticals. Thus, the mix of stellar ages influences a galaxy's appearance. A young, actively star-forming galaxy looks very different from an old, evolved system, precisely because of its stars. Over cosmic time, galaxies can even change type as their star formation slows. A disk galaxy may fade and redden into something more akin to an elliptical if starbirth ceases and its blue stars die out. The grand narrative of galaxy evolution is intimately tied to the cycles of star formation within. Now consider not just individual stars, but stars in pairs and groups. It may surprise you to learn that most stars in the sky are not solitary like our Sun, but part of binary or multiple star systems. Imagine two stars locked in a gravitational waltz, orbiting a common center of mass. Such binary star systems are incredibly common, by some estimates, more than half of all Sun, like stars, have a stellar companion. In these systems, stars can profoundly affect each other's evolution. Sometimes one star will swell into a red giant and transfer mass to its companion, an event that can spark explosive outbursts or novae. In fact, one type of supernova occurs in an elderly binary. A dense white dwarf star siphons gas from a companion until a runaway explosion is triggered, obliterating the white dwarf. These Type Ia supernovae are immensely important standard candles that have helped astronomers measure cosmic distances and the expansion of the universe. The discovery of the accelerating expansion of the universe, and hence dark energy, hinged on observations of distant Type Ia supernovae. Thus, an intimately interacting binary pair on the stellar scale produces a beacon visible across billions of light years, allowing us to gauge the universe's fate. In other binaries, two massive stars might evolve in tandem and eventually merge or collide. In globular clusters, such stellar collisions can produce the enigmatic blue straggler stars, stars that appear unexpectedly young and blue in a cluster of otherwise old stars. Blue stragglers are thought to form when two stars coalesce into a single, more massive star, effectively rejuvenating it. The result is a star that stands out as bluer and more luminous than it should for the cluster's age, a literal stellar oddball that reveals the cluster's dynamic past. The overcrowded cores of globular clusters facilitate such collisions, offering yet another example of how stellar interactions can yield peculiar outcomes. Some binaries consist of extremely exotic partners, for example, a neutron star or black hole orbiting a normal star. These systems can produce astonishing phenomena like X-ray binaries and even the recently detected gravitational waves. Picture a dense neutron star, essentially a city-sized atomic nucleus with the mass of the Sun, pulling gas off a companion star. As the gas spirals in, it heats up and emits powerful X-rays, making the binary shine brightly in X-ray light. In 1967, astronomers discovered pulsars. The first was affectionately nicknamed LGM-1 for Little Green Men 1, because its precise radio pulses were so mysterious, they were jokingly suspected to be alien signals. Soon, pulsars were understood as rotating neutron stars, the collapsed remnants of supernova explosions. In some binaries, two neutron stars orbit each other, gradually inspiraling as they radiate gravitational waves. In 2017, humanity observed for the first time the space-time ripples from such a neutron star merger, along with a dazzling multi-wavelength light show called a kilonova. That single event confirmed that neutron star collisions forge many of the universe's heaviest elements, and demonstrated how closely stellar death and cosmic alchemy are intertwined. Similarly, the first direct detection of gravitational waves in 2015 came from a merger of two stellar mass black holes, remnants of massive stars that had danced together until coalescing. These gravitational wave discoveries opened a whole new window on the universe, essentially hearing the sound of stars merging in the dark. Through binaries and their sometimes violent interactions, stars have enabled us to confirm Einstein's theories, understand extreme states of matter, and even create new fields of astronomy. While many stars live in pairs or clusters, our Sun stands alone. Yet the Sun is no less influential for its solitude. It anchors our solar system, and its steady light allowed life to flourish on at least one world. The Sun's story is still unfolding. About 5 billion years from now, it will swell into a red giant, becoming so large that it engulfs Mercury and Venus, and possibly Earth as well. By then, Earth will be a scorched cinder. As the Sun expands, it will also begin to blow off its outer layers. In its death throes, it may create a beautiful planetary nebula, a glowing shell of expelled gas, before finally settling down as a white dwarf. This stellar remnant, about the size of Earth but containing nearly half the Sun's mass, will slowly cool like a fading ember for trillions of years. That is the long-range fate of our sun and stars like it, to quietly shed their outer envelopes and leave behind dense cores. The galaxy will become littered with these white dwarfs, cosmic embers that, though faint, carry the memory of their progenitor stars. Even in death, stars continue to shape their surroundings. When a massive star explodes as a supernova, it leaves behind either a neutron star or a black hole. The expanding supernova remnant, a glowing cloud of ejected material E, can crash into surrounding clouds and trigger new rounds of star formation. Think of the Crab Nebula, the remnant of a supernova observed in 1054 AD. At its center lies a whirling pulsar energizing the nebula, and around it, the expanding filaments are rich in elements like oxygen, nitrogen, and iron, synthesized in the star's final moments. Those elements will eventually mix into interstellar space, seeding future molecular clouds. In this way, each supernova is both an ending and a beginning. An ending for a massive star, but a beginning for new stars that will one day condense from the enriched debris. Meanwhile, the neutron star left behind pours out winds of high-energy particles, sculpting and illuminating the nebula. A stellar corpse can thus continue to inject energy into the galaxy's ecosystem long after the star's death. Black holes, too, play a role. If a stellar mass black hole devours gas or stars, it converts that mass to energy, impacting the ambient gas. And on a galactic scale, supermassive black holes lurking in galaxy centers, themselves the end, products of stellar processes and mergers can profoundly influence star formation in their host galaxies by blasting out energy. But those supermassive black holes are a tale for another time. In our story, we focus on the stars themselves, the little black holes they leave behind, and how even those contribute to the cosmic tapestry. Consider for a moment the sheer number of stars out there. Our Milky Way alone holds on the order of 100 to 400 billion stars. It's a figure almost beyond comprehension. And yet, the Milky Way is just one of perhaps hundreds of billions of galaxies in the observable universe. If each of those has 100 billion or so stars, you get numbers like 10 more 22 stars in the observable universe. That's a 1 with 22 zeros after it, a quantity of stars truly staggering to contemplate. Each of those stars is a potential sun, perhaps with its own family of planets. In recent decades, we've learned that planets abound around other stars. The once singular idea of another solar system has given way to the realization that planetary systems are commonplace. Using missions like Kepler and TESS, astronomers have detected over 5,000 confirmed exoplanets so far, and counting. Statistics indicate that perhaps 1 in every 5 sun, like stars, harbors an Earth-sized planet in its habitable zone. This means when you gaze up at the night sky, statistically the nearest sun, like star with an Earth-ish planet, might be only a dozen light years away, practically next door on the cosmic scale. Planetary systems come in a dizzying variety: hot Jupiters, skimming their stars' surfaces, multi-planet systems packed in tight orbits, planets around double stars, and even planets orbiting the crushed remnants of dead stars. There are even planets wandering alone in the dark of interstellar space. Stars and planets are inseparable companions in the cosmic story, and just as stars give birth to planets, planets can influence stars in subtle ways. Take our solar system. The sun's activity and stability have been key to life's development on Earth. Our sun is a rather steady star, but not all stars are so calm. Many young stars and red dwarfs are highly variable and prone to flares. Variable stars in general constitute a broad category, including stars that intrinsically pulsate, erupt, or have eclipsing companions, causing dips in light. These variations have made certain stars vital tools for measuring cosmic distances. For instance, the Cepheid variables, luminous pulsating supergiants, have a well-defined relationship between their pulsation period and true brightness. Discovered by Henrietta Leavitt over a century ago, this relationship allows astronomers to determine a Cepheid's distance by comparing its known true brightness to its observed brightness. Using Cepheids as standard candles, Edwin Hubble measured the distance to the Andromeda galaxy in the 1920s, discovering that Andromeda lay far outside our Milky Way, thus proving that the universe is populated with myriad galaxies. Later, Cepheids and Type Ia supernovae would help establish that the universe is expanding and, in fact, accelerating in its expansion due to mysterious dark energy. It's poetic that the rhythmic beating of variable stars' light has served as a cosmic yardstick, allowing us to map the universe at large. A throbbing Cepheid in a distant galaxy becomes a beacon, indicating that galaxies' distance, and hence offering insight into the scale of the cosmos. Not all variable stars are so regular and helpful. Some are downright capricious. There are flare stars that can double in brightness in minutes, eruptive variables like young stellar objects that burp out bursts of light as they gulp down fresh gas from their surroundings, and giants like Mira, a star in Cetus that pulsates over many months, varying so much that it can nearly disappear from view and then return. And who could forget the recent drama of Betelgeuse, the red supergiant shoulder of Orion? In late 2019, Betelgeuse dimmed startlingly, losing 2/3 of its brightness, causing speculation that it might be about to explode as a supernova. Observations eventually indicated that Betelgeuse had likely ejected a cloud of dust that temporarily obscured its light from our vantage point. By mid-2020, Betelgeuse returned to normal. This episode was a vivid reminder that stars are dynamic, evolving entities, not static points of light. Betelgeuse is expected to go supernova sometime in the next 100,000 years, a blink of an eye in cosmic terms, and when it does, it will light up our sky brilliantly for weeks, a spectacular final act for a star perhaps 15,020 times the Sun's mass. If we're lucky enough to witness it, that supernova will be a momentous event in human skywatching history. But even short of such cataclysms, the variability of stars teaches us about their inner workings. Through the field of astroseismology, astronomers study tiny pulsations in stars to infer their internal structures, analogous to how geologists use earthquakes to probe Earth's interior. Our Sun, too, has a mild 11th-year cycle of activity, modulating its sunspots and flares, which subtly affects solar output. Thankfully, the Sun's variability is slight. A more erratic star might have made Earth's climate far less stable for life. Stars, then, are creators, testers, and timekeepers of the universe. They create the elements that form planets and people. They test the laws of physics in extreme conditions, from nuclear fusion in cores to relativistic speeds in neutron stars. They serve as timekeepers by revealing cosmic distances and ages through their life stages and variable rhythms. And collectively, stars brighten the universe, turning the primordial darkness into a cosmos of light and color. It is sobering and fascinating to realize that the universe's era of starlight is, in a sense, a finite chapter. We live roughly in the middle of this chapter. For billions of years before stars, the universe was dark, and trillions upon trillions of years in the future, after the last stars have flickered out, the universe will go dark again. But right now, and for many eons to come, it is the age of stars. An age in which galaxies sparkle and life has the opportunity to arise on warm, sunlit worlds. The story of stars is also the story of continuity and renewal. Massive stars live fast and die young, but in doing so, they trigger new growth around them. We see this in regions like the Carina Nebula, where the death of one generation seeds nebulae that birth the next. In a spiral galaxy's life, waves of star formation move through the disk, often stimulated by spiral density waves or past encounters with other galaxies. Our own Sun likely formed in a cluster with dozens or hundreds of other stars about 4.6 billion years ago, possibly triggered by a nearby supernova explosion that compressed our natal cloud. Traces of that supernova may be preserved in certain isotopes found in meteorites from the early solar system. Thus, the Sun and planets might owe their existence to the death of a long-gone massive star. Indeed, each of us carries the ashes of ancient supernova inside our bodies. The iron in your blood was forged in a star that exploded billions of years before the Sun even existed. In a very literal sense, stars are our cosmic ancestors. As we look ahead, what new revelations about stars await us? We stand in an exciting era of astronomy. The James Webb Space Telescope is now peering into the deep cosmos, possibly capturing light from some of the first galaxies and stars that formed over 13 billion years ago. Already, Webb has identified candidate galaxies so far away that they challenge our understanding of how quickly stars and galaxies could have formed. In the coming years, Webb may indirectly detect evidence of population 3 stars, or at least constrain their properties by observing the distant galaxies they inhabit. On the other end of the spectrum, Webb and other observatories are turning their gaze to exoplanet atmospheres, reading the fingerprints of molecules like water vapor, carbon dioxide, and methane as starlight filters through alien skies. In 2022, JWST made the first clear detection of carbon dioxide in an exoplanet's atmosphere, a proof of concept for the detailed atmospheric analysis of potentially habitable worlds in the future. We are learning to read the chemical weather reports on planets dozens of light years away, an astounding development. Future missions will go even further. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys of the Milky Way's center, potentially discovering thousands of new exoplanets through microlensing and mapping out the distribution of stars and dark matter with high precision. The European Extremely Large Telescope, a 39-meter behemoth currently under construction, will in the next decade directly image some exoplanets and dissect the light of stars in distant galaxies, perhaps even detecting biosignature gases on rocky planets around nearby stars. It is mind-boggling. We are on the cusp of potentially finding evidence of life beyond Earth by examining starlight passing through a distant planet's atmosphere. Should we succeed, it would be a profound confirmation that we are not alone, all made possible by the interplay of stars and their planets. Even without finding life, the future of stellar astronomy is bright. New observatories will allow us to watch stars in real time in unprecedented ways, catching the precise moment a star goes supernova in our galaxy, or detecting the subtle vibrations of stars across our galaxy to decode their ages and compositions. We might witness phenomena we've only theorized, perhaps the birth of a black hole accompanied by a flash of neutrinos and gravitational waves, or the mergence of 2 white dwarfs into a new star or a supernova. We may even discover new classes of stars. Who knows? Throughout history, whenever we have opened new eyes on the universe, we've stumbled upon surprises. There could be rare types of stellar objects out there awaiting discovery, stars powered by exotic physics, or stars caught in transitions never before seen. The universe tends to be creative with its use of the physical laws. From the first luminous beacons that banished the cosmic night, to the ordinary middle-aged sun that sustains life on a blue planet, to the spectacular supernovae and gravitational wave chirps that herald stellar deaths, stars have been the main protagonists in the cosmic drama. They are the alchemists that forged the elements, the lighthouses that guide our explorations, and the engines driving the evolution of galaxies. As we float here on our tiny world, bathing in the gentle sunshine of our star, we remain intimately connected to the lives of stars across the universe. Every atom of calcium in your bones was fused in a star that lived long ago and far away. Every gentle sunset tinged with reds and oranges is a reminder that our sun, too, will one day swell and cast a red hue over the sky of whatever beings inhabit Earth in the distant future. Yet even as individual stars perish, the universe ensures the torch of light is passed on. New stars ignite from the ashes, continuing the cycle. And so, the cosmic roles of stars are as profound as they are varied. Stars are creators of light, of elements, of new beginnings. Stars are destroyers. In their violent ends, they can obliterate companions or outshine entire galaxies for a time. Stars are storytellers. Their compositions and motions recount the history of their galaxies. Stars are guideposts. Their steady pulsations and explosions have built our cosmic distance ladder and expanded our knowledge of the universe's expansion. Stars are nurturers, providing warmth and energy to any orbiting planets, and perhaps nurturing life. It is often said that without stars, the universe would have remained a dull, cold fog of hydrogen and helium. There would be no planets, no complex chemistry, and certainly no people to wonder at it all. Indeed, without the stars, the universe would lack its narrative spark. Our exploration of the stars deepens our connection to the cosmos. When we look up on a clear night and see the Milky Way's band of light, we are seeing the integrated glow of billions of distant suns, many of them older, many younger, each on its unique journey from birth to death. Among them are red giants, white dwarfs, neutron stars, perhaps even black holes quietly lurking. All of them together create the shimmering tapestry of the night sky. As we conclude this chapter of the documentary, let's reflect on the awe that stars inspire. For thousands of years, humans have looked to the stars for constancy, for navigation, for myths and meaning. Only in the last century or so have we truly grasped what they are. Nuclear furnaces, balanced by gravity, simple in their basic principles, yet endlessly diverse in their outcomes. And only in the last few decades have we come to see the universe on the largest scales and realize the full extent of the stars' role in shaping everything. The saga of stars is ongoing. Even now, new stars are being born in dusty nebulae. Old stars are blowing themselves apart. Binary stars emerging. Planets are coalescing around nascent suns. Life might be evolving in some distant solar system under the light of an alien star. And photons that left stars billions of years ago are just now reaching Earth, bringing us news from across the universe. With each advance in technology, we become better listeners and observers of the stars' messages. In the near future, we might map the surfaces of stars' light, years away, or detect the faint whispers of stars collapsing into black holes across the universe. And someday, perhaps, we will travel to other stars, our descendants, voyaging across interstellar space to touch those points of light that have beckoned for ages. For now, we continue to study and marvel. The stars have been our beacons, our ancestors, our catalysts. They will continue to shine for billions of years, but not forever. So it is a privilege to exist in this epoch of glittering skies. As our story winds down, step outside on a dark night and look up. Each star you see is part of a grand cosmic ecosystem. Some of those stars are likely orbited by planets you cannot see, perhaps harboring beings who look back at our sun as just another point of light in their sky. In the end, stars connect us across the gulfs of space and time. They are the universals, appearing in the sky of any planet in any galaxy, adhering to the same physics, telling variations of the same tale. This is the cosmic role of the stars, to light up the universe, to forge atoms from the raw stuff of the Big Bang, to sculpt galaxies, to cradle planets, and to continuously renew the cosmos. They are the glittering thread woven through the fabric of space, time, binding the universe together in light. And as long as stars shine, the universe will not be a lonely, lifeless place, for their light creates the possibility for beauty, complexity, and life. The story of stars is the story of how the universe, once a primordial soup of particles, became self-aware through creatures like us. We are the children of the stars, and through us, the stars know themselves. In the ever-continuing cycle of cosmic evolution, the stars have truly shaped the evolution of the universe, and they will continue to do so far into the future. So, whenever you stargaze, remember, you are watching creation in action, witnessing the ongoing drama that made all of existence possible. The tale of the stars is the tale of us all, a story still unfolding, written across the sky in the light of a billion suns. Silence, darkness, no stars, no ground beneath your feet, and perhaps not even the flow of time, just an infinite, motionless night. Imagine a void, with no up or down, no sound or motion. In that profound quiet, before anything begins, we find a fundamental question taking shape. What is the dark, yawning space that stretches out in all directions? Not the stars or planets that speckle it, but the space itself. The black canvas on which all cosmic lights are hung. What is space, when it stands alone, empty of all things? Since ancient times, people have looked into the night and pondered the void. Many mythologies begin with a great empty darkness from which creation arises, a cosmic egg in a vast sea, or a formless chaos giving birth to the world. In a way, modern science echoes those old intuitions. We too speak of an initial emptiness that blossomed into the universe we know. We usually imagine space as nothingness, a vacant expanse separating the stars. Even scientists once assumed it was merely an empty stage. In the 19th century, many thought an invisible ether must fill the void, a mysterious medium to carry light. But every experiment to detect this ether failed. Light needed no carrier at all. It moved through pure vacuum. Space, it seemed, could be truly nothing. And yet, if you listen closely to the silence, you may sense something more subtle. The void is not truly void. The darkness is not truly nothing. Space is a presence, an invisible fabric that underlies everything. It is quiet and transparent, so easy to ignore, yet it is real, physical, and dynamic. Space isn't an empty backdrop, but an active, ever-present matrix. It can bend, it can stretch, it can ripple. About a century ago, our picture of space underwent a profound change. Experiments and new ideas revealed that space is not a fixed, unchanging void at all. It can warp and even participate in the cosmic dance. Gravity, we learned, is not a mysterious pull through nothingness, but a bending of space itself by mass. Space and matter interact continuously. Space is like the quiet canvas that holds a painting, or the pause that makes music melodic, an unseen framework that underlies and gives form to everything. Imagine placing a heavy ball on a taut rubber sheet. The sheet stretches and sags under the weight. In much the same way, anything with mass, a planet, a star, a galaxy, presses on the fabric of space. Space curves gently around it. What we feel as gravity is not a pull through emptiness, but the tendency of objects to slide down those curves. The Earth circles the Sun because the Sun dents the space around it, like a large marble sitting on a stretched cloth. Earth is not tethered by invisible strings. It is caught in the Sun's invisible indentation in space-time, moving along a curved path that to us appears as an orbit. In short, mass shapes the geometry of space, and space guides the motion of mass. Even light, which has no mass at all, follows the curves of space. Over 100 years ago, during a total solar eclipse, astronomers noticed that stars appearing near the eclipsed sun were slightly out of place. Their light had bent on its journey to us, detoured by the sun's warped space. It was a dramatic confirmation that space itself, curved by the sun's presence, was guiding the starlight. Today, we regularly use this effect, called gravitational lensing, to observe distant galaxies. A massive cluster of galaxies can act like a cosmic lens, its curved space bending the light of even more distant objects behind it. Sometimes we see a single galaxy smeared into an arc, or even a perfect ring of light encircling a closer galaxy cluster that is acting as the lens. These mirages are the unmistakable signature of space, behaving like a gigantic lens, bending and focusing the paths of light. Through these rings and arcs, we see space itself revealing its curvature to our eyes. If space can bend, it can also stretch. Indeed, the fabric of space has been steadily expanding since the primordial beginning of the universe. Distant galaxies are not just flying away through space. The space between us and them is itself growing. Early observers noticed that the light from remote galaxies is shifted toward the red end of the spectrum, as if the wavelengths have been stretched out. The farther a galaxy, the more its light is redshifted. The straightforward explanation is that space itself is expanding, carrying galaxies apart like raisins embedded in rising dough. Over billions of years, this expansion has enlarged the distances between galaxy clusters immensely. Another useful image is to picture space as the two-dimensional surface of a balloon, with galaxies like ink dots on that surface. As the balloon inflates, the dots move farther apart from each other. No single dot is the center of the expansion. Every dot sees the others receding. Likewise, in our three-dimensional space, every galaxy observes other galaxies rushing away. If we rewind this expansion in our minds, we find that in the distant past, everything was closer together. Galaxies crowd nearer, stars huddle closer. Far enough back, all the matter and light in the universe was crammed into a much smaller volume than today, a state of incredible density and heat. Space itself was compact and blazing with energy. There was a time when the entire young universe was like a hot, glowing fog. Imagine being present in that early inferno. No distinct stars or structures, just a blazing soup of particles and light everywhere you look. An intense white-orange glare filling all of space. As space expanded and thinned out, that searing brilliance faded to a gentler afterglow. Even now, space carries a memory of that fiery beginning. When we point sensitive instruments to the sky, we detect a faint glow of microwaves coming from every direction. This is the afterglow of the primordial fireball, the cosmic microwave background. It is the light from a time about 380,000 years after the Big Bang, when space had cooled enough for atoms to form and for light to travel freely. Since then, those light waves have been stretched by the ongoing expansion of space until they are microwaves, cooled to only a few degrees above absolute zero. Every patch of space is filled with this soft whisper of ancient light. It is almost perfectly uniform and smooth, but has tiny fluctuations, little freckles of slightly warmer and cooler spots, corresponding to minuscule density variations in the early universe. Those slight differences, on the order of only 1 part in 100,000, became the seeds for galaxies and clusters later on. It's as if the walls of the universe still faintly remember their incandescent youth. This ancient light also gives us clues about the overall shape of space. By studying subtle patterns in the microwave background, scientists have learned that on the largest observable scales, space is remarkably flat in its geometry. In a curved universe, those patterns would appear distorted, larger or smaller than expected, much as drawings on a balloon change size when the balloon is inflated. But observations show no such distortion. The angles of those primordial patterns add up just as they would in flat, Euclidean space. For example, in a universe shaped like a 3D sphere, a closed universe, two initially parallel beams of light would eventually converge and meet. and traveling in a straight line long enough could, in theory, loop you around to your starting point, just as an airplane circling the Earth arrives where it began. In a saddle-shaped or open universe, parallel beams would diverge and triangles would have angles summing to less than 180 degrees. But our measurements show nothing of the sort. This suggests that space, as far as we can measure, is not curved into a giant sphere or warped into an endless saddle. Instead, it stretches out in all directions without substantial overall curvature. Space is, to the best of our knowledge, flat and likely unbounded, or so vast that it might as well be infinite. It might extend infinitely, or perhaps it wraps around on a scale so colossal we cannot detect it. But within our cosmic horizon, space behaves like an endless level plane. To achieve such vast flatness and uniformity, the universe likely underwent an extraordinary growth spurt at the very dawn of time. According to the theory of cosmic inflation, a fraction of a second, on the order of 10 over 32 seconds or less, after the Big Bang, space itself expanded at a mind-boggling rate, doubling in size over and over in the blink of an eye. In that brief moment, what had been a microscopic region inflated to astronomical scales. A region smaller than a proton might have stretched to the size of a galaxy in an instant. This rapid stretching would have smoothed out any curvature or clumps, explaining why space now appears so flat and even on large scales. During inflation, tiny random quantum fluctuations, little blips of density in the microscopic early universe, were blown up to enormous sizes. Quantum fluctuations inherent to space itself, magnified to cosmic proportions, became the seeds of future structures. Regions of the young universe that had just slightly more matter or energy became, after inflation, entire huge regions with that slight edge. Those minuscule differences, perhaps only a few parts in 100,000 in density, gave certain patches of space a head start in gravitationally attracting matter. As the universe aged, those patches grew into the first galaxies and clusters. In this way, inflation planted the seeds of cosmic structure. The slight differences from one place to another, once infinitesimal, became the blueprint for all the galaxies, clusters, and voids that would later develop. Space, by expanding so fiercely, essentially cast the dice for the universe's future architecture, turning tiny quantum wrinkles into the grand pattern of stars and galaxies we observe today. When this furious burst of expansion ended, the energy driving it did not simply vanish. It transformed, heating the universe with a burst of radiation and particles. In essence, when inflation stopped, space unleashed its pent-up energy, igniting the hot Big Bang fireball that people often think of as the beginning of the universe. From that point onward, space continued to expand, but at a calmer pace, filled with a blazing plasma that would eventually cool into atoms, gas, stars, and galaxies. The rapid inflationary expansion set the initial conditions, and the slower expansion that followed allowed the cosmos as we know it to emerge. Inflation also opens the door to a startling idea: a multiverse. If the inflationary expansion happened in our region of space, it might have happened, or be still happening, in others. Some theories suggest that inflation never completely stops everywhere. While it ended in our patch, allowing our Big Bang and galaxies to form, in other regions space might still be inflating, or might have ended at a different time. Each of these regions could become its own universe, a bubble with its own galaxies, and perhaps even different physical constants. Our observable universe would then be just one bubble in a limitless foaming sea of universes. We have no way to directly see these other bubbles. They lie beyond any light we could ever receive. But the multiverse concept shows how our conception of space may extend even beyond the bounds of our own universe. Space, in this grand view, is an ever-expanding ocean, spawning countless cosmic islands. Whether this is true or not remains speculative, but it stretches our imagination of what space could be, not just the stage of one universe, but perhaps a prolific generator of many. Over billions of years following inflation, gravity worked on the tiny density variations left in the fabric of expanding space, drawing matter into clouds and clumps that would ignite as the first stars and galaxies. Galaxies pulled together into groups and clusters, and these linked up via filaments of gas and dark matter, forming a vast cosmic web. On the largest scale, the universe looks like a spider web or a sponge, dense clusters of galaxies connected by thread-like filaments, with enormous dark voids in between. Those voids, immense bubbles, millions of light years across, nearly empty of galaxies, are the regions that gravity emptied out as it drew matter into the filaments. In other words, most of the universe's volume consists of these yawning voids, with the galaxies tracing lacy patterns along their boundaries. It's a breathtaking structure, the invisible scaffolding shaped by gravity out of the expanding fabric of space, with over 80% of the volume of the universe contained in those silent voids. The lights of the stars and galaxies stand out like glittering nodes, but it is the darkness between them that dominates by volume. Now picture yourself in the middle of one of those cosmic voids, utterly removed from any galaxy. You are floating in intergalactic darkness, light years from the nearest star. Around you, the darkness is nearly absolute. Perhaps a faint, ghostly smudge of a distant galaxy is barely visible in one patch of sky, and another dim glow in the opposite direction. But to your unaided eyes, it would mostly be pure black. The nearest substantial galaxy could be tens of millions of light years away, so far that its light is unimaginably feeble. You are, for all practical purposes, alone in a silent, endless night. This is space at its most austere, a volume of the universe almost entirely devoid of matter. And yet, even here, space is not truly empty. A stray hydrogen atom might drift by now and then, or a thin breeze of particles from some far-off galaxy cluster might waft through. You would also be bathed in the ever-present microwave background radiation from the Big Bang, though you wouldn't sense it without instruments. In this void, you can viscerally feel that space is something real, a vast container with you at the center and almost nothing else around. It's a haunting, beautiful solitude. Such voids are the dark wombs of the cosmos, within which the bright filaments of the cosmic web are suspended. Gravity's architecture, the cosmic web of filaments and voids, is heavily influenced by a form of matter we cannot see, dark matter. Decades ago, astronomers measuring the speeds of stars in galaxies discovered a surprise. In galaxies like our Milky Way, the outer stars orbit the center far faster than expected, based on the visible stars and gas alone. They should have been flung off into space, but they remained bound. It was as if an extra unseen mass was providing the gravitational pull to hold them in. Likewise, galaxies in rich clusters move as though there is much more mass present than we can account for with the observed galaxies and hot gas. And when we observe gravitational lensing by a cluster, the bending of light is far stronger than visible matter alone can explain. All of this evidence points to a vast amount of invisible mass enveloping galaxies and clusters. We call this mysterious substance dark matter. It neither emits nor absorbs light, making it effectively invisible to our telescopes. Yet it outweighs ordinary matter by a factor of about 5. Dark matter forms huge halos around galaxies, extending well beyond the visible stars. Every galaxy, including our own, is embedded in a cocoon of this invisible material. Entire galaxy clusters are swathed in massive clouds of dark matter. Its gravity is what helped pull normal matter into the filaments of the cosmic web in the first place. Without dark matter's guiding gravitational pull, the universe's large-scale structure would have formed much more slowly and differently. We cannot see dark matter directly, but we see its imprint. Space curves around it, and galaxies move under its gravitational influence. Through these effects, the hidden scaffolding of dark matter in space becomes perceptible. Space is quietly filled with an unseen mass that shapes the universe profoundly. In the late 20th century came another revelation. The expansion of space is accelerating. After gravity built the cosmic web, one might expect that over time the pull of all those galaxies on each other would slow the expansion of space. And for billions of years, it likely did slow. But to great astonishment, we have found that in the last few billion years, the expansion of the universe has begun to speed up again. Distant galaxies are receding faster and faster as time goes on. Space is expanding not only steadily, but with an ever-increasing pace, as if some mysterious force is pushing it outward. We give the name dark energy to this unknown cause of cosmic acceleration. Unlike dark matter, which adds gravity, dark energy seems to act as a kind of anti-gravity on vast scales, a subtle pressure embedded in the fabric of space that drives it to expand faster. As space grows, more of this repulsive effect appears, since dark energy is thought to be a property of space itself, pushing galaxies apart with increasing strength. Today, dark energy dominates the universe's energy balance. Roughly 70% of the total contents of the cosmos appears to be this shadowy influence, with dark matter making up most of the rest. The ordinary matter, the stars, gas, dust, planets, and us, accounts for only a few percent. In an ironic twist, the emptiest thing, space, contains the majority of the universe's energy in this form. The silent void has an energetic underpinning that shapes the cosmos. What this means for the far future is profound. As space expands faster and faster, galaxies that are now visible will eventually slip beyond our cosmic horizon, their light stretched and diminished until they vanish from view. In tens or hundreds of billions of years, everything outside our local group of galaxies will have moved out of reach. The universe will appear to whoever remains as an empty void, with only the local galaxies, perhaps merged into one, in view. For example, in about 100 billion years, the galaxies of the Virgo cluster and beyond may be so far that their light never reaches the Milky Way region. After many hundreds of billions more years, even the nearest large galaxy, Andromeda, now destined to collide and merge with our Milky Way long before then, and its remnants would be far beyond detection. The expansion of space will carry all other islands of matter irretrievably away. What will the cosmos look like then? In that deep future, the observable universe will become dark and empty, with only faint whispers of local starlight remaining. Perhaps an astronomer living in that far future era on some distant world would peer into the sky and see nothing beyond her own galaxy. She might point her telescope outward and find endless blackness in every direction. All other galaxies would have faded beyond reach or redshifted into obscurity. She would have no way of knowing that a vast cosmos full of galaxies had ever existed. The cosmic truth we know today, that space teems with billions of galaxies, would be hidden from her by the relentless expansion of space. That future astronomer might conclude that her galaxy was the entire universe, a tiny island adrift in infinite nothingness. For us living in the present cosmos, the discovery of dark energy is a humbling reminder that what we once took to be empty nothingness can control the destiny of everything. The silent space between galaxies turns out to hold a secret power that shapes the entire evolution and future of the universe. Space, the quiet stage, has proven to be the hidden protagonist of the cosmic story. Before we return home, let us take an imaginary journey back through the cosmic expanse. Picture yourself out at the edge of a great cluster of galaxies, where hundreds of galaxies shimmer around you like a glittering swarm. Now you begin to travel back toward our own galaxy. As you move, galaxies drift past, scattered in the vast darkness. You glide along one of the filaments of the cosmic web that leads to the Milky Way, passing other island universes along the way. In the distance ahead, a faint band of light comes into view. the combined glow of billions of stars. Our Milky Way, seen from afar as a hazy, spiral disk of light. You approach it, crossing the immense gulf of intergalactic space. Now you plunge into the outskirts of our galaxy, rushing past sparse outer star clusters and the wispy halo of tenuous gas. The star density increases around you as you enter the Milky Way's disk. Entire clusters of young stars drift by. Great nebulae, stellar nurseries, glow softly in pink and blue. By the time you near the inner regions, stars surround you like a sparkling ocean. You weave through a spiral arm, passing magnificent blue-white giants and red supergiants, skirting around clouds of interstellar dust. In the distance, you spot a modest yellow star, our Sun, coming into view. As you draw closer, you see it is accompanied by planets orbiting in the plane of a thin, flat solar system. You sweep past the orbit of Jupiter, then Mars, and now the blue sphere of Earth appears. At this scale, it is a tiny, fragile-looking bead of blue and white, shining against the blackness. You home in on it, watching its oceans and clouds resolve into clarity. In moments, the planet looms large, its atmosphere a glowing thin shell. You slip gently into that atmosphere, experiencing the rush of air as you descend, and finally come to rest on Earth's surface, back to the soft familiarity of ground beneath your feet. Your fantastical voyage from the end of the universe to our home is complete. Now, having roamed the vast reaches of the cosmos, let us gently return our focus to something more intimate, the space around and within us. We leave the clusters of galaxies and zoom back toward a single galaxy, our Milky Way, and then to a particular star, our Sun, with its family of orbiting planets. Between those worlds stretches millions of kilometers of space, populated only by sparse dust and the thin wind of charged particles from the Sun. Closer in, we see the blue marble of Earth, surrounded by the gauzy blue halo of its atmosphere. From high above, Earth appears as a delicate blue-white sphere hanging in the blackness. Our atmosphere, a thin film of air and cloud, clings to its surface and gradually merges into space. Only a few hundred kilometers up, the air becomes so tenuous that space begins. Beyond that, the sky fades to black. In truth, there is no sharp boundary where space starts. The air just thins more and more until there is effectively none. But effectively, just above the blue sky, the true vacuum of space begins. Only a fragile veil of atmosphere separates us from the cosmic void. There, in low Earth orbit, astronauts aboard space stations witness directly the stark contrast between the bright Earth below and the utter blackness above. They float in microgravity, essentially falling around Earth, immersed in space. When they look up, away from Earth, they see endless darkness spotted with stars that do not twinkle because there is no air up there to flutter their light. The sun shines fiercely without the softening filter of atmosphere, and the divide between day-lit Earth and night-shadowed Earth is a sharp line across the globe. Those astronauts live on the very boundary of space, inside a thin bubble of air in their spacecraft that separates them from the vacuum outside. They often describe the experience as deeply humbling. Above them, an infinite void. Below them, the jewel of Earth with its thin blanket of air. During spacewalks, when they step outside into the vacuum, wearing only a protective suit, they can feel the profound silence and isolation of space. No sound, no breeze, only the distant curve of Earth and the raw, brilliant stars. For them, space is not a theoretical concept, but a palpable reality. They understand in their bones that space is here, around us, an ever-present ocean, just a breath beyond our daily reach. We descend back to the surface now. Picture yourself standing on a quiet night field, looking up at the stars. Although you feel solid ground underfoot and air on your skin, You are as much in space as an astronaut floating in orbit. The space around you is simply filled with a thin mixture of gases, our atmosphere. If you could magically remove all that air, the vacuum that remains would be continuous with the vacuum between the planets and stars. There is no wall or border between space down here and space up there. It is one connected expanse. The same space that stretches between galaxies is present in the room around you, between the walls and among the molecules of air. We truly have never left space. We live at the bottom of a shallow ocean of air, but that ocean is itself embedded in space. People often talk about going into space as if it's somewhere else, but space is already here. Step by step, as you climb a mountain or rise in a balloon, the air thins and space reveals itself. Astronauts in orbit are not in a different realm. They have merely ascended above most of the air, into the naked vacuum that was there all along. Space is not distant. It is the backdrop of our existence, even here on Earth. Even our everyday experiences are dialogues with space. Take a breath. You inhale molecules of air that moments ago were scattered across the room, and you exhale molecules that will disperse outward. In doing so, you are stirring the space around you. The air filling your lungs quickly mixes and returns to the atmosphere, ultimately diffusing into the great expanse. In a very real sense, space is the medium through which life interacts with the world. Every movement you make is a displacement in space. Every sound you hear travels to you through vibrating molecules in space. Out in the near-total vacuum beyond Earth's atmosphere, there is no air to carry sound. In space, no one would hear you scream. It is truly silent out there. Every sight you see is brought to your eyes by light crossing space. Space is not an abstract backdrop to life. It is intimately involved in every aspect of our being. Consider even more deeply, you yourself are largely made of space. The atoms in your body are mostly void, their mass concentrated in tiny nuclei, and their size defined by electrons moving through emptiness. If all the empty space in your atoms were somehow removed, you would collapse into a speck far too small to see. And of course, without that space, you wouldn't exist as a living being at all. It is the spacious architecture of your atoms that allows them to bond into molecules, and molecules to build cells, and cells to form a living organism. Thus, space is inside you as much as you are in space. It provides the room that your particles and forces need to operate. We begin to see a pattern from the vast distances between galaxies down to the tiny gaps within atoms. Space is there, quietly doing its work. It provides room for structure to exist, for planets to orbit, for light to travel, for atoms to join and form molecules. The emptiness is not a flaw or an absence. It is an essential ingredient. It allows separation and form. Without the gulf of space within each atom, there could be no distinct atoms and no chemistry, no solid matter as we know it. Without the reaches of space between stars, gravity could not isolate individual worlds where life might arise. Space is the great enabler, the silent canvas that allows matter to take shape and motion to have meaning. Just as a clay pot's usefulness lies in the empty space it encloses, the utility of the cosmos lies in its gaps and hollows. An empty cup holds water. The emptiness within an atom allows it to bond with others. In both cases, what is not there enables what is there to function. And what about space at even smaller scales, far smaller than an atom, smaller than the tiniest subatomic particle? Here we approach deep mysteries. Physicists suspect that if you zoom in far enough, space itself becomes turbulent and uncertain. On the scale of the Planck length, about 10 to 35 meters, the very concept of distance might break down. Space might dissolve into a kind of quantum foam, with the smooth fabric of space-time becoming frothy and indeterminate. At that scale, according to some ideas, tiny bubbles of space-time could appear and vanish, and geometry itself might fluctuate wildly. Wheeler, a physicist, famously imagined the scene as the quantum foam, a churn of space-time at the smallest scales. Over sufficiently small distances and brief moments, the smooth geometry of space and time could erupt into a storm of random fluctuations. Imagine zooming into what looks like a smooth photograph, only to find it grainy with pixels at a certain magnification. These fluctuations could be large enough, on those scales, to cause significant departures from the smooth space-time we perceive at human scales, giving space a foamy, jittering character when examined ultramicroscopically. With our current technology and understanding, we cannot probe such minute scales directly. Our best theories, quantum mechanics and general relativity, don't play nicely together at this extreme, so we don't yet have a clear picture of what space truly looks like at the Planck scale. It's possible that space-time is not fundamentally smooth. It might be made of countless tiny units or threads. There is no definitive reason that space needs to be perfectly continuous. Perhaps, in a full theory of quantum gravity, space-time would consist of many small, ever-changing regions where space and time themselves blur and fluctuate. It's a mind-bending idea. The familiar continuity of space might, under magnification of 1033, break into a ceaseless fizz of tiny distortions and ephemeral particles popping in and out of existence. Yet black holes are not absolutely black. Quantum theory predicts that the vacuum near the event horizon of a black hole seethes with particle-antiparticle pairs. Occasionally, one particle from such a pair can be pulled into the black hole while the other escapes. To an outside observer, the black hole appears to emit a faint trickle of particles, a phenomenon known as Hawking radiation. Over inconceivably long periods, this process can cause a black hole to slowly evaporate, leaking its mass back out into space. This is another reminder that even the empty space near a black hole is full of activity. The vacuum isn't void at all. Its quantum fluctuations can have tangible effects, bleeding away the black hole's mass bit by bit. In this way, space acts as both giver and taker, swallowing light at the horizon, yet furtively returning energy to the universe through quantum processes. One place where we suspect this quantum nature of space becomes crucial is inside black holes, those mysterious abysses formed from collapsed stars. A black hole is a region where space is curved so extremely that once anything, matter or light, falls in, it cannot escape. The boundary around a black hole is called the event horizon. At that boundary, space is rushing inward at the speed of light, like a waterfall of space-time cascading into the hole. If you approach the horizon, time slows relative to the outside world, and the pull of gravity, the curvature of space, becomes overwhelming. To a distant observer, you would appear to slow and dim, never quite falling in, as your final light waves get stretched and weakened, a strange visual consequence of the way space and time warp. Beyond the horizon, all paths lead further inward, deeper into the hole. As you fall inside a black hole, you would experience space rushing you inexorably toward the center. According to general relativity, at the very center lies a singularity, a point of infinite density where space and time, as we know them, ends. In truth, this singularity is likely where our current understanding fails. Gravity is so extreme and the scale so tiny that quantum effects should dominate. Here, the smooth fabric of space might tear or blend with the quantum foam. The distinction between space and matter could blur. We don't yet have a theory of quantum gravity to tell us exactly what happens in such an intense intersection of the very large and the very small. Does space cease to exist as a meaningful concept at the core of a black hole? Are there atoms of space-time or quantum threads knitting things together beyond our view? We simply don't know. The laws of physics as we have them break down in these conditions. Physicists have proposed bold ideas to reconcile these deep conflicts. One radical suggestion is that space and time might not be fundamental at all, but rather emerge from something more basic and abstract. Some research hints that quantum entanglement, the ghostly interconnection between particles, may knit together the fabric of space itself. In certain theoretical models, the geometry of a region of space can be described entirely by the information, the entanglement connections, on its boundary. This is known as the holographic principle, suggesting that our three-dimensional space might in some way be a projection from information encoded on a distant two-dimensional surface. It's as if space could be woven from quantum threads of information. Another idea is that space-time is composed of tiny, discrete units, sometimes envisioned in approaches like loop quantum gravity, so that on the smallest scale, space is more like a woven lattice or network. These concepts are still speculative and hard to test, but they share a poetic point. They hint that space, for all its apparent continuity, might be an emergent illusion, like a tapestry that looks smooth from afar, but up close is made of fine threads. If so, there could exist degrees of freedom or building blocks of the universe more fundamental than space and time. What is space, truly? It may be that our familiar space is just the visible frosting on a much deeper reality. Facing these profound questions, humanity has responded by inventing clever ways to probe the nature of space. We have built powerful telescopes that peer across billions of light years, effectively allowing us to look back in time and see the young universe when it was filled with hot plasma and newly formed galaxies. We have launched observatories above our atmosphere to measure the cosmic microwave background with exquisite precision, mapping its faint ripples to decode how space expanded and what it contains. We have devised experiments on Earth to test the nature of the vacuum. For instance, sensitive laboratory apparatus has confirmed the Casimir effect, detecting the slight pressure of vacuum fluctuations pushing two plates together. We smash particles together in giant accelerators, momentarily concentrating tremendous energy into tiny volumes of space, to glimpse how nature behaves at the highest energies and smallest scales. This endeavor led to the discovery of the elusive Higgs field that permeates space and endows particles with mass. We have even detected the subtle ringing of space-time itself using gravitational wave observatories like LIGO. These giant laser interferometers can sense when space stretches and squeezes by less than a trillionth of a centimeter as a gravitational wave passes. The first such detection in 2015 came from two merging black holes and was heard as a faint chirp, literally the sound, after conversion, of space briefly vibrating from a cosmic collision. Since then, we have caught multiple cosmic events via gravitational waves, black holes swallowing each other, neutron stars colliding and sending tremors through space. It's a completely new way of listening to the silent universe, using space itself as our messenger. We have also physically journeyed into space, albeit only a small distance so far in cosmic terms. Our robotic probes have ventured beyond the planets, sampling the environment of space directly. The Voyager 1 and 2 spacecraft, for example, have traveled beyond the influence of our sun's solar wind and entered interstellar space, the space between the stars. They confirmed that even the emptiest regions of our galaxy are not entirely empty. They contain traces of very thin plasma, ionized gas, and high-energy cosmic rays. Voyager 1, now over 23 billion kilometers away, is humanity's farthest messenger. It is sailing through the cold, silent void, reporting back that even out there, far from any star, there are a few atoms per cubic centimeter and faint whispers of magnetic fields and radiation. Its journey reminds us that space is not a distant void we go to. It's the ocean we've always been swimming in, now stretching out to greater and greater depths. We are not outsiders to the universe's expanse. We are an integral part of it. We move through space. We depend on it. We are composed of it. In a sense, we, conscious beings, are space's way of observing itself. the universe contemplating its own vastness through our eyes. From the space between galaxies to the space inside your chest, it is one continuous fabric. The next time you gaze up on a clear night and marvel at the darkness between the stars, remember that that darkness is not empty. It is the same space that cradles you, extending through and around you always. We tend to think of ourselves as down here and space as out there. But in truth, we have always been in space. From the moment of our birth, we have been enveloped by space. Space is not a distant domain only astronauts visit. It is the vast, subtle medium in which we live and breathe. When you look up at the night sky, you are looking into an extension of your own surroundings. The air ends not far above your head, and then space continues, unbroken, to the ends of the universe. So, what is space? It is not a mere nothingness, not a sterile void. It is the gentle scaffolding that holds all of creation. It is a medium that can bend and ripple, a vast field that carries light and nourishes the formation of stars. Space is the silence that allows the music of existence to be heard. It is the canvas on which the galaxies are painted. And yet the canvas itself has texture and influence beyond what our eyes see. Space is the invisible architecture of the universe, the foundation that connects all things. It is often said that nature abhors a vacuum, but in truth, nature uses the vacuum, space, as the foundation for everything. Without space, there would be no room for light to travel, no separation for objects to exist apart, no time for events to unfold. Space is not the absence of things. It is the presence that allows things to be. It is the very possibility of anything and everything. As our journey through darkness and light comes to an end, we return to that initial quiet question and find a profound answer. Space is not an emptiness to be feared, but a presence to be revered. It is the quietly fertile nothing that makes everything possible. We float in it, we are made of it, and we are forever embraced by it. The invisible architecture of the universe surrounds and sustains us. Space is the darkness that cradles the stars, the silence that gives meaning to sound, the stillness that makes motion possible. It is the vast, living fabric in which the story of the cosmos and our own story is written. Space is the womb of the universe, the canvas of creation. It is not an absence, but the gentle yet all-encompassing presence that allows all things to be. In the beginning, there was darkness. For a long age after the birth of the universe, no stars shone, no galaxies twirled. Only darkness and silence stretching across an unfathomable expanse. The cosmos was newborn and without form, filled with diffuse clouds of hydrogen and helium gas, remnants of the Big Bang. There were no twinkling lights, no warmth, only the faint afterglow of creation cooling into night. Imagine that primordial darkness, a universe waiting, quiescent and still, with all its future potential sleeping in invisible clouds. But even in that silence, gravity was at work. Slowly, imperceptibly, it drew the primordial gas into filaments and clumps, coaxing the first structures to form in the void. Over eons, these clumps grew denser and hotter at their centers. Deep within one such gathering of gas, pressure and heat built until something new and miraculous occurred. Nuclear fusion ignited. There, in the bleak darkness, a tiny point of light flared into being. The first star had been born. In that moment, the universe was no longer lightless. A spark had appeared in the cosmic night. With that first star, the cosmic dawn broke. One solitary star poured out light and heat, pushing back the blackness around it. And soon, another star lit, and then another, scores of them, flickering on in the cosmic night. What had been endless darkness was now speckled with faint starlight. These first stars were unlike the stars we know today. They were giants of pristine hydrogen and helium, born in a virgin cosmos. They burned with brilliant blue-white fire, immensely hot and massive. Their intense ultraviolet light flooded into the surrounding gloom and began to clear away the primordial fog of neutral hydrogen that filled space. For the first time, light moved freely through the cosmos, illuminating it on a grand scale. The cosmic dark ages were ending. The universe was beginning to reveal itself in starlight. These first stars lived fast and died young. After only a few million years, brief by cosmic standards, their central fuel was exhausted. In their cores, they had fused hydrogen into helium and helium into carbon and other heavier elements, forging the first atoms of carbon, nitrogen, oxygen, and more. When fusion could proceed no further, the balance that held them up faltered. The stars met their end in colossal explosions. One by one, the primordial giants tore themselves apart as supernovae. Each such explosion was titanic. Momentarily, a single star's death could outshine an entire galaxy. The night that had been gently lit by starlight was suddenly ablaze with a ferocious flash. Then, as the supernova faded, darkness returned. But it was not the same darkness as before. Now, it was enriched by the scattered ashes of stars, the gaseous debris of those first supernovae, carrying newly forged elements mixed back into the cosmic gas, seeding the universe with the ingredients for future worlds. Meanwhile, gravity continued its creative work on larger scales. The first stars had formed in small protogalactic clumps, and gravity drew these clumps together. They merged and coalesced into the first galaxies, swirling assemblies of stars, gas, and dark matter. The once empty universe was now dotted with infant galaxies, and each new galaxy sparkled with the light of millions of stars. Over billions of years, galaxies grew by merging with each other and forming new stars within. The cosmos transformed from a dark, simple expanse to a richly structured tapestry. By a few billion years after the beginning, the cosmic web of galaxies stretched across space, filaments of glimmering light tracing gravity's hand. Generation after generation of stars continued to be born and die within these galaxies, steadily enriching and shaping them. The universe's early thin gases had become a complex network of stellar cities, glowing with billions of points of light. Let us drift into one such galaxy, a spiral galaxy not unlike our own Milky Way, at a time when the universe is mature and full of stars. Within one of its graceful spiral arms lies a vast, cold cloud of molecular gas and dust, tens of light years across. It is dark and opaque, a silent nebula hiding new wonders inside. This is a stellar nursery, a place where new stars will be born. For ages, this cloud has floated in the galactic disk, nudged by passing spiral density waves and perhaps stirred by ancient supernova shockwaves. Now, regions within it begin to collapse under their own gravity. Deep inside, dense knots of gas form, each destined to become a star or a group of stars. All through the cloud, multiple embryos of stars are taking shape, though they are hidden from view by the dusty shroud. In one region, a particularly dense clump, perhaps a few dozen times the mass of our Sun, contracts and fragments. At its center, material compresses into a smaller, hotter protostar. Change is coming to the darkness of this nebula. At first, the forming star is shrouded. It is a protostar, not yet fully born, growing as it pulls gas from the surrounding cloud. It spins faster as it contracts, and a rotating disk of gas and dust forms around it. Twin jets of hot gas shoot out from its poles, tunneling through the cloud. Deep inside, the temperature climbs higher and higher. For tens of thousands of years, a mere moment in cosmic time, this protostar gathers mass in the darkness, heating up steadily. When its core temperature reaches about 10 million degrees, a great transformation occurs. Hydrogen nuclei begin to fuse into helium. In a sudden burst of energy, true starlight ignites in the core. The protostar has become a star. Outward pressure from this newborn star's core now halts any further rapid collapse. The star's fierce light and stellar winds blow away the cocoon of dust and gas that enveloped it. At last, the new star emerges from its birth nebula, announcing itself with brilliant light. The surrounding leftover gas, bathed in the star's intense ultraviolet radiation, begins to glow. What was once an invisible, cold cloud now shines as an ionized nebula, like a cosmic neon sign, its hydrogen gas fluorescing pink and red. A dark corner of the galaxy has given birth to a beacon of light. In the surrounding cloud, other newborn stars are likely emerging as well, turning the nebula into a cradle of suns. Indeed, stars are often born in litters. The collapse of one part of a cloud usually means many fragments produce protostars in the same region. As our star bursts forth, it is joined by dozens or hundreds of sibling stars, all coming to life together from the same cloud. Together, they form a young star cluster, a sparkling group of newborn suns of various masses. They blaze hot and blue, their combined radiance blowing the remaining nebular material into filaments and wisps. One can imagine the scene, where there was darkness and dust. Now there is a cluster of radiant stars, their light reflecting and refracting in the thinning veil of gas. The stellar nursery has become a celestial nursery rhyme of light, a beautiful, chaotic region celebrating the arrival of new stars. For a time, these siblings remain clustered, bound by the gentle gravitational pull they exert on each other. They drift together through the galaxy as a loose family known as an open cluster. In the cluster's early life, it is a stunning jewel box of brilliant stars, all relatively close in space. Yet, over hundreds of millions of years, this family will gradually disperse. Gravitational nudges from passing stars and clouds, as well as internal interactions, will cause members to wander away one by one. The cluster's members, once tightly knit, become strays, settling into their own orbits around the galaxy, mingling with billions of other solitary stars. This is the fate of most open clusters. They are transient gatherings that eventually dissolve into the galactic population. Our own sun likely shared this fate. It was almost certainly born in a cluster with many siblings, stars that formed from the same cloud some 4.6 billion years ago. Over time, that original cluster dissolved. Today, the sun roams the galaxy alone, and the stars that were born alongside it have long since scattered. A few of the sun's lost siblings may have been tentatively identified by their chemical signature, but most are strangers now far across the sky. Still, it's a profound thought. The sun's family of origin has dispersed, yet the galaxy is now sprinkled with those related stars, each carrying the same ancestral imprint in their atoms. In a sense, every star eventually becomes an orphan, blending into the vast community of the Milky Way. Some star clusters, however, are so massive and tightly bound that they can survive for billions of years. These are the globular clusters, ancient, spherical hordes of stars that reside in the outskirts, halo, of galaxies. A globular cluster might hold hundreds of thousands of stars crammed into a ball only a few hundred light-years across. The stars inside are extremely old, many formed during the early eras of the galaxy. They shine mostly with a warm reddish glow, having long ago lost their bluer, short-lived members. The stars in globular clusters are almost pure hydrogen and helium, containing only tiny traces of heavier elements, which tells us they were born before later generations of stars had seeded the galaxy with metals. They are truly relics of the distant past, cosmic time capsules unchanged for eons. If you could stand on a planet inside a globular cluster, the night sky would be a breathtaking spectacle. Thousands of stars would crowd the heavens, many so bright that even at night they could cast subtle shadows. There might be no true darkness at all. Your sky would be awash with perpetual starry twilight. These ancient clusters have witnessed nearly the entire history of the universe. Some of the stars shining around you in that cluster may have been burning since shortly after the galaxy itself formed. Globular clusters endure as splendid beacons on the fringes of galaxies, their stars bound together in a tight gravitational embrace for billions upon billions of years. Now let us return to our star, the one we followed out of its nebula. It has left its nursery and cluster behind, or its siblings have all drifted away. The star has entered the long, steady adulthood of stellar life. Deep in its core, hydrogen fusion generates a steady outpouring of energy. This energy travels from the core through radiative layers and convective currents, and finally radiates from the star's surface as light and heat. Gravity pulls inward on the star's mass, but the pressure of hot gas and the continuous fusion-powered radiation push outward. These forces balance perfectly. The star settles into a stable state known as the main sequence, where it will spend the majority of its life shining at a nearly constant brightness for eons. It is as though the star has found harmony, a peaceful equilibrium in which it neither collapses under gravity nor erupts from internal fire, but simply glows steadily. Our Sun is in this very phase of life. It is a middle-aged main sequence star, quietly fusing hydrogen into helium in its core, as it has for about 4.5 billion years, and will continue to do for roughly another 5 billion. Day after day, it shines with reassuring consistency, its energy nurturing the planets orbiting it. We live in the warm embrace of a stable star. The sunlight that bathes Earth each day is the product of that core fusion, photons freed from the sun's interior after thousands of years of random walk and an 8-minute sprint across space to our world. This steady radiance has allowed life to arise on Earth, anchoring our existence. The sun, in all its ordinariness, means everything to us. Yet the sun is just one of countless stars on the main sequence, doing the same quiet work across the galaxy. Even the sun has its subtle rhythms. Its surface seethes with convection, and dark magnetic blemishes called sunspots come and go. Approximately every 11 years, the sun's magnetic activity cycles, leading to periods of many sunspots and flares followed by lulls. Sometimes great arcs of plasma erupt from its surface in solar flares or coronal mass ejections, sending streams of charged particles into space. When these particles wash over Earth, they can spark auroras that dance in our polar skies, a vivid reminder that our seemingly gentle sun has its storms. Still, these variations are minor on the scale of the sun's total output. To our eyes and lives, the sun remains a stable beacon. It is a calm star by cosmic standards, and that calm has been essential for life on Earth to thrive over geological timescales. Not all stars enjoy such tranquility or longevity. The destiny of a star is determined largely by its mass at birth. Mass is the master parameter that dictates a star's temperature, brightness, and lifetime. A very massive star lives dramatically. It burns its fuel at a furious rate, shines brilliantly, and dies young. A small star lives cautiously. It sips fuel slowly, glows gently, and may outlive all other stars. Consider a star 10 times the sun's mass. Its core temperatures are far higher, and it will blaze blue-white, pouring out energy hundreds of thousands of times faster than the sun. But it might last only 20 million years before exhausting its core fuel. Now consider a star 1/10 of the sun's mass, a red dwarf. It is cool, perhaps 3000 K at the surface, and dim, maybe 1/1000th the sun's luminosity. It will burn its hydrogen so frugally that it can live for hundreds of billions or even trillions of years. The universe itself is not old enough for any such star to have died yet. None of the red dwarfs born at the dawn of time have even begun to flicker. In short, massive stars are the sprinters of the cosmos, and red dwarfs are the marathon runners. Astronomers classify stars by their spectra and temperature. The hottest, most massive stars are O-type, glowing bluish-white and searingly bright. After O come B and A types, still extremely hot and white. F and G-type stars, our Sun is a G-type, are intermediate, white to yellow in color and moderate in heat. K and M stars are cooler, orange to red in hue, including the countless red dwarfs. This sequence, O, B, A, F, G, K, M, is essentially a temperature scale from the fiercest blue-white stars to the faintest red stars. And indeed, the night sky shows this variety. Some stars shine with an icy blue tint, others with a golden glow, and some with a faint reddish light. Each color is a clue to a star's inner furnace. A blue star is like a roaring fire. A red star is like a warm ember. The cosmos offers a grand palette of stellar colors and intensities. The sizes of stars also span a tremendous range. Some red supergiant stars have bloated to astonishing dimensions, as much as 1,000 times the Sun's radius. If one of those sat where our Sun is, its swollen atmosphere would extend beyond the orbit of Mars, perhaps even reaching Jupiter. By contrast, the smallest stars, just above the threshold for sustained fusion, are only a bit larger than the planet Jupiter. One of these tiny red dwarfs, while containing perhaps 8% of the Sun's mass, might measure only 1/10 of the Sun's width. Between these extremes lie stars of every conceivable size, from giant stars big enough to engulf orbits of planets, to humble dwarves barely bigger than gas giant planets. The diversity is staggering. And if an object is smaller still, below about 8% of the Sun's mass, it never becomes a true star. It becomes a brown dwarf, a failed star. Such an object doesn't reach the core temperature needed for sustained hydrogen fusion. A newborn brown dwarf may briefly fuse a little deuterium, a heavy form of hydrogen, or simply radiate leftover heat from its gravitational contraction. But before long, it settles into a life of slowly cooling and fading. Brown dwarfs are like cosmic embers. They glow faintly in red or infrared light, but no fire rages within. They fill the gap between the largest planets and the smallest stars. In the galaxy, there may be as many brown dwarfs as stars, lurking dimly in the darkness, detectable only by sensitive infrared eyes. They remind us that nature's categories are fluid. There is a continuous spectrum from planets to stars, with brown dwarfs bridging the two. To the unaided eye across human lifetimes, most normal stars shine with a steady light. But many stars are not truly constant. Some vary in brightness in subtle or dramatic ways. Some stars pulsate in and out like cosmic heartbeats. A classic example is a Cepheid variable, a bright giant star that rhythmically swells and shrinks, causing its brightness to rise and fall over a period of days or weeks. When it expands, its surface cools and it dims slightly. When it contracts, it heats up and brightens. These pulsating stars are so regular that astronomers use them as distance markers. Their pulse period relates to their true luminosity. So by observing their cycle, we can deduce how far away they are. They literally blink out a Morse code that we have learned to read, helping us measure the universe. Other stars vary more erratically. Young stars, still surrounded by disks of gas, can flicker as they accrete material, or as clumps of dust periodically obscure them. Some mature stars erupt in flares, especially red dwarfs, which can unleash powerful stellar flares that make the star momentarily much brighter. Even our Sun is slightly variable. Over its 11-year sunspot cycle, its energy output changes by a fraction of a percent. And in old age, many stars become variable again. Red giants often pulsate with large amplitudes, like mirror variables, taking many months to cycle through a dimming and brightening. Such an elderly star might expand and contract so much that it visibly changes brightness over the course of a year, shedding its outer layers with each pulse. In some cases, a star's light is not changing because of its own behavior, but because of an external effect. Consider binary star systems aligned in our line of sight. When one star passes in front of the other, it eclipses its companion. From Earth, we see the combined light dip periodically, even though each star's intrinsic output is steady. These eclipsing binaries produce regular patterns of dimming and brightening, a stellar blink that can be clockwork precise. By studying such systems, astronomers can learn the sizes of stars and their orbits. In fact, the discovery of planets orbiting other stars often comes from a similar effect. A planet passing in front of its host star causes a tiny eclipse, a minute drop in the star's brightness. Sensitive telescopes can detect that dip, revealing the presence of a world we cannot otherwise see. In this way, the light of stars encodes the presence of their companions, be they other stars or orbiting planets. Indeed, many, perhaps most, stars are not solitary like our Sun, but part of binary or multiple star systems. Two stars bound together will orbit a common center of gravity, like dancers linked by an invisible string. If they are well separated, each evolves individually. But if they orbit closely, their lives can become intertwined in remarkable ways. Imagine a close binary where one star ages faster and swells into a red giant, while the other is still a smaller main sequence star. As the giant grows, its outer layers draw ever closer to the companion star. Eventually, the giant's gravity can no longer hold on to those distended layers. Its material starts flowing onto the companion. A stream of gas begins to pour through the inner Lagrange point, the gravitational gateway between them, forming a luminous accretion disk around the smaller star. Matter spirals in, heating up and glowing brilliantly. The giant star, losing mass, shrinks back somewhat, relieved of its burden, while the companion star gains fresh fuel and becomes hotter or more active. This mass transfer dramatically alters the fate of both stars. If the receiving star in such a scenario is a white dwarf, the dense core of a previously sun-like star, the story takes another turn. The gas dumped onto the white dwarf piles up on its surface. Over time, perhaps years or centuries, enough hydrogen accumulates on the white dwarf surface to trigger a sudden burst of fusion. In a flash, the layer of accreted gas ignites and detonates, causing the white dwarf to erupt in a nova. The star system that was faint brightens drastically for a little while, as the white dwarf's surface explodes in a thermonuclear flash visible across light years. After venting that energy, the white dwarf settles down and the cycle can begin anew if more gas comes in. In this way, a close binary can produce repeated novae like a recurring stellar heartbeat of explosive energy. In some cases, the white dwarf accumulates too much mass from its companion, beyond a critical limit, about 1.4 times the mass of the Sun. Then the entire white dwarf is overwhelmed by runaway fusion and detonates in one titanic explosion, a Type Ia supernova. In that instant, the white dwarf is obliterated, and a fireball of debris expands outward. Such a supernova can briefly rival a whole galaxy in brightness. Nothing of the white dwarf remains, only a rapidly expanding cloud of ash, rich in iron and nickel, hurtling through space at thousands of kilometers per second. These Type Ia supernovae are incredibly important standard candles in astronomy, yet behind their brilliance is the quiet story of a binary companionship that went to the extreme. Other binary destinies include outright mergers. If two stars in a binary spiral closer, perhaps due to gravitational wave emission or interactions with other stars, they can eventually collide and coalesce. Two main sequence stars merging will produce a single, more massive star, often with a spectacular transient event. Astronomers have observed luminous red novae, believed to be the signature of merging stars. The pair slowly draw together, then suddenly brighten with a red glow as they meld into one. The result might be an oddly bloated star or a fast-spinning object, but a new single star nonetheless. If, on the other hand, the binary is two neutron stars, the dense remnants of supernovae, their merger is even more dramatic. They collide and merge into either a heavier neutron star or a black hole, releasing a burst of energy that can include intense gamma rays and gravitational waves, literally a ripple in space-time that can be felt across millions of light years. Such a merger also forges heavy elements, like gold and platinum, in profusion, seeding the surrounding space with these precious materials. Thus, even in their deathly collision, stars create and share new riches with the cosmos. For long periods in between such events, a solitary star like our Sun just keeps shining steadily. But eventually, even the most stable stars must face an end to their fuel. Our Sun, for instance, after roughly 10 billion years of main sequence life, will deplete the hydrogen in its core. So what happens when a star runs out of its most basic fuel? The answer unfolds in stages, heralding the transition to a star's old age and death. For the Sun and stars of similar mass, this final chapter is both gentle and beautiful. For more massive stars, it is violent and spectacular. When a star like the Sun exhausts the hydrogen in its core, fusion in the core ceases, but fusion still goes on in a shell of hydrogen around the now inert helium core. With the core no longer generating outward pressure, it begins to contract under gravity. That contraction releases gravitational energy, which heats the core and the surrounding shell of hydrogen. The hydrogen shell, now hotter and under higher pressure, burns even more vigorously than the core did. The increased energy output pushes the star's outer layers outward. The star's envelope balloons to enormous proportions. As it expands, the star's surface cools because the same energy is radiating from a much larger area, and its hue shifts toward red. The star has become a red giant. Our Sun will go through this transformation, swelling perhaps 100 times its current diameter. In those far future days, the Sun's reddish orb could engulf Mercury and Venus, possibly even reaching close to Earth's orbit. Even if Earth is not swallowed, the Sun's expanded atmosphere and intense heat would scorch our planet barren. In any case, the inner solar system will be radically transformed. A person, if somehow observing from a safe distance, would see the Sun change from a small yellow disk to a vast, ruddy sphere that dominates the sky. The once stable star becomes a bloated giant, its core an intensely hot, contracting ball of helium ash. Its outer layers diffuse and cool. Yet paradoxically, the Sun will shine more brightly overall during this red giant phase because its enormous size more than compensates for the cooler surface. It will be majestic and terrifying all at once. Inside the core of the red giant Sun, temperatures continue to climb as the core contracts under gravity's relentless squeeze. When the core reaches about 100 million degrees Celsius, a new kind of fire is kindled, helium fusion. 3 helium nuclei begin fusing together to form carbon, in a process called the triple alpha reaction. In stars like the Sun, this onset of helium fusion can occur very suddenly in what's known as a helium flash, releasing an enormous burst of energy in a matter of minutes. However, that energy mostly goes into lifting and expanding the core, not into blowing the star apart. The Sun will then settle into a new equilibrium, a helium-burning star. The core expands and cools slightly after the helium flash, and the star's outer layers contract a bit from their extreme red giant state. The Sun will become a somewhat smaller, though still large, yellow-orange giant, with a core quietly fusing helium into carbon and oxygen. This helium-burning phase is much shorter than the hydrogen-burning main sequence, perhaps only a few tens of millions of years for a star like the Sun. Eventually, the helium in the core is exhausted as well. Now the core of the Sun will be made primarily of carbon and oxygen, the ashes of the helium-burning phase. The core again lacks an energy source and begins to contract yet further. For a star of the Sun's mass, it will not reach the temperature needed to ignite carbon fusion. Fusion will continue only in shells around the core, a shell of helium fusing into carbon just outside the core, and a shell of hydrogen fusing into helium above that. The star responds by expanding again, It enters a second red giant phase, the asymptotic giant branch phase, swelling even more dramatically than before. The Sun will become extremely large and luminous, but also unstable. Its outer layers are only loosely bound now, and strong pulsations set in, causing the star's brightness to vary and its layers to puff outward and then fall back cyclically. During this time, the Sun, or any star in this phase, will begin to undergo significant mass loss. Each pulsation in the star's envelope helps throw some gas into space. The star also generates a slow but intense stellar wind, a stream of particles that drags away the star's outer atmosphere. The once robust star is quite literally blowing itself apart, bit by bit. Over tens of thousands of years, the Sun will shed a substantial fraction of its mass. Those outer layers drift away into space, forming an expanding cloud of gas around the star. As more material is lost, eventually the star's hot, naked core becomes exposed, illuminating the receding layers from within. The Sun will no longer be a red giant, but a small, incredibly hot star at the center of a growing gaseous shell. What forms is one of the most beautiful phenomena in astronomy, a planetary nebula. Despite the name, a planetary nebula has nothing to do with planets. The term arose because through early telescopes, these round gas shells looked a bit like planetary disks. It is the glowing remnant of a star's atmosphere, cast off into space. The emerging stellar core at the center may be tens of thousands of degrees hot and emits strong ultraviolet radiation. This radiation ionizes the expanding shell of gas, causing it to fluoresce in vibrant colors, soft greens and reds from oxygen and hydrogen, for example. Planetary nebulae come in many shapes: spherical shells, ring-like structures, hourglass forms, even complex symmetrical patterns sculpted by magnetic fields or binary companions. They last only tens of thousands of years before the gas disperses into the interstellar medium. But while they shine, they are among the most beautiful sights in the cosmos, the very soul of a star laid bare in color and light. Our Sun's planetary nebula might appear as a shimmering halo in the sky, a final gorgeous adornment to mark the end of the Sun's life as a star. This nebula will expand and dissipate into the interstellar medium over perhaps 10 or 20,000 years, mixing its enriched gases with the cosmic clouds that will someday form new stars. At the center of the planetary nebula remains the core of the star, a dense, hot sphere about the size of Earth, composed mostly of carbon and oxygen. This is the final state of the star, a white dwarf. A white dwarf no longer has fusion occurring in its core. It is supported against further collapse by quantum degeneracy pressure of electrons, a rather exotic form of pressure that doesn't depend on heat. When it first forms, a white dwarf is extremely hot, well over 100,000 K, and it glows white-blue with residual heat. Over billions of years, it will radiate that heat away and cool down, becoming yellow, then red, and eventually fading to black, an exotic cold crystal of carbon and oxygen in the far future, sometimes poetically likened to a giant diamond in space. However, the universe is not old enough for any white dwarfs to have cooled to the black dwarf stage yet. Even the oldest white dwarfs still shine faintly with leftover heat. The white dwarf that remains of our Sun will be incredibly dense. More than half the Sun's mass is crammed into a sphere the size of Earth. A single teaspoon of its material would weigh billions of kilograms. It's an object not unlike a planet in size, yet containing the mass of a star. It will slowly cool and dim, perhaps taking tens of billions of years to become truly dark. In the meantime, the legacy of the Sun lives on. The planetary nebula it ejected enriches the galaxy with elements like carbon and nitrogen that were made in its core, and the white dwarf stands as a testament to the star that once was. This is the gentle end that awaits stars of modest mass, a quiet shedding of beauty and a final fade into darkness. But what of the giants? The massive stars that lived only a few million years on the main sequence and then grew into supergiants. They face a far more dramatic end, A star significantly heavier than the Sun, say 8 times the Sun's mass or more, will go through similar stages, hydrogen to helium, helium to carbon, and so on. But it doesn't stop at carbon. After the red supergiant phase begins, its core, much more massive than the Sun's ever was, keeps contracting and heating. It ignites carbon fusion when helium is depleted. Then it forms a core of oxygen neon magnesium, which in turn, when exhausted, leads to neon burning, producing oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Finally, silicon burns into iron. The star develops onion-like layers. At the center, an iron core. Around that, a shell of silicon fusing to iron. Above that, a shell of oxygen fusing to silicon. Then a carbon-burning shell. Then a helium-burning shell. Then a hydrogen-burning shell at the exterior. Each stage of fusion releases energy, except the last. And for a time, each supports the star. But the cycles accelerate. Carbon may burn for 1,000 years, neon for a year, oxygen for mere months, silicon for days. The iron core grows rapidly as silicon burning dumps iron ash into it. And then the star reaches the final limit. The iron core grows so large, around 1.4 solar masses, that it can no longer support itself. Iron is a nuclear dead end in a star's life. Fusing iron atoms doesn't yield energy, it consumes energy. So once the core is largely iron, the star has no further fuel to tap that can hold up the core. In the heart of the massive star, in the span of a second or less, everything changes. The iron core, about the size of Earth and incredibly dense, billions of kilograms per cubic meter, collapses under its own weight. Electrons and protons in the core are crushed together, forming neutrons and releasing neutrinos. The core's collapse accelerates until it is stopped by the most fundamental forces, the strong nuclear force and neutron degeneracy pressure. What was an iron core a few thousand kilometers across is now a ball of neutrons, only perhaps 20 kilometers in radius, a nascent neutron star. The infalling material of the star's inner layers crashes onto this incompressible core and rebounds. A powerful shockwave forms, but at first it stalls within the star. Then, aided by an immense flood of neutrinos pouring out of the core, trillions of neutrinos blasting through each square centimeter, depositing energy, the shockwave regains strength and punches outward. In a magnificent catastrophe, the star explodes. This is a core collapse supernova, the violent death of a massive star. In that instant, the star is obliterated. The outer layers are catapulted into space at a significant fraction of the speed of light. The energy released is almost unfathomable. For a few brilliant days or weeks, the exploding star can outshine the entire galaxy that once humbly hosted it. If such a supernova occurred within, say, 100 light-years of Earth, it would appear brighter than the full moon and could potentially wreak havoc on our biosphere. But typically, these explosions occur safely distant, turning up as new stars in the sky, recorded by astonished observers across history. In 1054 CE, Chinese astronomers recorded a guest star that remained visible in daylight for weeks. This was a supernova in our own galaxy. Even today, nearly 1,000 years later, we see the expanding debris of that explosion as a faint, glowing cloud in the constellation Taurus. In 1604, European observers witnessed another brilliant new star in the Milky Way, which was likewise a supernova. And in 1987, a supernova blaze in a neighboring galaxy, the Large Magellanic Cloud, was visible to the naked eye. These rare events left a deep impression on those who saw them. When the supernova's glare finally subsides, it leaves behind a rapidly expanding shell of gas and dust, a supernova remnant, and, at its heart, the crushed core, either a neutron star or a black hole, depending on the mass. The supernova remnant is a spectacular thing in its own right. The ejected gases, enriched with heavy elements forged in the final moments of the star, like nickel, cobalt, and iron, rush outward and collide with the surrounding interstellar medium. They form glowing filaments and shock fronts that can remain visible for tens of thousands of years. Telescopes today reveal delicate tendrils and wisps of glowing gas in these remnants, beautiful and haunting, the ashes of a star spread across light years. These filaments gradually mix with the general galactic gas. The elements they carry, oxygen, carbon, silicon, iron, and more, become part of the raw material for new stars and planets. Thus, a supernova is both an ending and a new beginning. The star is gone, but its material is now free to join new cosmic structures and even one day to become part of new living worlds. At the center of a supernova remnant lies whatever remains of the star's core. If the progenitor star was not too extremely massive, perhaps up to 20-25 solar masses, this remnant will be a neutron star. If the star was more massive, the core collapse likely continued until a black hole formed. Let us consider the neutron star case first. A neutron star is one of the strangest objects in existence. Imagine compressing the sun into a ball only 20 kilometers across, the size of a city. At that density, a single teaspoon of neutron star material would weigh billions of tons on Earth. The gravity at its surface is so intense that if an object were dropped from 1 meter above the surface, it would hit the surface in a microsecond, releasing as much energy as a large bomb. Yet, despite these extreme properties, neutron stars are real, and we detect them regularly. Many neutron stars reveal themselves as pulsars. When a massive star's core collapses to a neutron star, it often retains much of its rotational momentum in a greatly shrunken form, so it spins extremely fast. Imagine a star spinning once every 30 days, like our Sun, collapsing to an object only 20 kilometers wide. Conservation of angular momentum would make it spin perhaps hundreds of times per second. Indeed, many neutron stars spin at least dozens of times per second when born. They also can have intense magnetic fields, trillions of times stronger than Earth's. These magnetic fields, anchored in the dense star, accelerate particles and create beams of radiation from the neutron star's magnetic poles. As the neutron star spins, these beams sweep around like the light from a lighthouse. If Earth lies in the path of these beams, we observe a pulse of radio waves, light, or X-rays with each rotation, hence the name pulsar. Some pulsars spin with astonishing speed. A millisecond pulsar can rotate over 700 times in 1 second. Their regular flashing is so precise that pulsars rival atomic clocks in stability. They are nature's metronomes. When pulsars were first discovered, their signals were so regular that some jokingly labeled them LGM for little green men, suspecting an intelligent origin before natural causes were understood. Now, pulsars help us probe extreme physics and even detect gravitational waves indirectly through changes in their orbits. A lone neutron star will gradually cool and slow down over millions of years, becoming fainter and less active. Some neutron stars have magnetic fields so strong that they occasionally fracture their own crusts in starquakes, producing bursts of high-energy radiation. These are called magnetars, and they are the most magnetic objects known. But even magnetars eventually calm as they lose energy. In the fullness of time, a neutron star might become a cold, inert sphere of neutron matter, drifting through the galaxy. Yet it will remain, essentially forever, as a remnant of its parent star, a cosmic tombstone marking where a mighty star once shone. If the core of the collapsing massive star was above the neutron star limit, around 2-3 solar masses, gravity wins an even more final victory. The core continues to shrink past the neutron star stage and becomes a black hole. This is the most extreme outcome of stellar death. The entire mass of the core collapses to an infinitely small point, as far as our physics can describe, and a region of space-time is created from which nothing can escape. A black hole is not a solid object, but rather a region, bounded by the event horizon, beyond which escape velocity exceeds the speed of light. Whatever remains of the star's core resides in that region, forever cut off from communication. In effect, the star's mass punches a hole in the fabric of the universe. All we can observe is the gravitational field it leaves behind, and perhaps X-rays or jets from material spiraling into it from outside. If the black hole is alone, it may be nearly impossible to detect, as it emits no light of its own. But if it has a companion star or is surrounded by gas, that material can form a hot accretion disk as it funnels into the black hole. Friction and extreme gravity heat the disk to millions of degrees, causing it to glow in X-rays. Sometimes, as the disk material swirls inward, the black hole's magnetic and rotational effects can launch jets of particles at nearly light speed from the poles. These relativistic jets can extend for light years, a ferocious announcement of a black hole's presence. Yet, despite such displays, the black hole itself remains unseen. Only its influence on nearby matter and space-time is evident. It's a silent well in the fabric of reality, a gravitational ghost marking where a star once radiated. In either case, neutron star or black hole, the core collapse supernova has transformed the star and distributed almost all of its substance back into the cosmos. And that is perhaps the greatest significance of these mighty events. They are creators in destruction's clothing. In the furnace of the supernova, and in the neutron star mergers we discussed, many of the universe's heaviest elements are forged. The gold in your jewelry, the iodine in your thyroid, the uranium in the Earth's crust. These atoms were synthesized in the intense crucibles of exploding or colliding stars. The calcium in your bones was formed in a long-dead red giant. The iron in your blood was made in the core of a massive star and distributed by a supernova. Stellar lives and deaths are directly responsible for the elemental richness that enables planets and life. Without generations of stars cooking simple hydrogen into heavier elements and then ejecting them, a planet like Earth could never exist. The universe's first stars had no solid planets around them. There was nothing solid to form rocks or life. It took billions of years of alchemy in stars to brew the ingredients of biology and geology. Thus, each generation of stars leaves a legacy for the next. The gas between stars, the interstellar medium, grows increasingly enriched. Young stars that form now have subtle amounts of iron, silicon, oxygen, and other elements mixed into the primordial hydrogen and helium because they draw from clouds seeded by prior supernova and stellar winds. Our Sun, for example, contains about 2% of these heavier elements, metals in astronomer speak, whereas a first-generation star had virtually none. That 2% might sound small, but it's critical. It's the material that formed Earth and our bodies. In a cosmic sense, later stars carry the DNA, so to speak, of earlier stars within them. Every star that dies writes part of its story into the next generation's composition. We see this continuity everywhere. In regions where massive stars recently died, we often find new star formation triggered by their explosive energy, like flowers blooming after a forest fire. The shockwave from a supernova can compress nearby clouds of gas, spurring those clouds to collapse into new stars. The intense radiation from young hot stars in turn can erode and sculpt neighboring clouds, sometimes stimulating further clumping and star birth at the cloud's edges. It's an intricate cycle, star death leading to star birth, a cosmic phoenix rising from the ashes. Through this ongoing cycle, the galaxy's supply of gas gradually diminishes, but it ensures that successive generations of stars are born with the gifts of their ancestors already inside. By now, it's clear that stars are not isolated points of light. They are the central actors in the great story of the cosmos. They sculpt galaxies with their collective light and their winds and explosions. They forge nearly every chemical element heavier than helium in their cores or in their fiery deaths. and they create the conditions for planets to form around them in the leftover disks of their birth. From those planets, beings like us can eventually emerge, beings made of star stuff, who then look back and ponder the stars. Our Earth coalesced around a second or third generation star, the Sun, about 9 billion years into the universe's timeline. It carries in its rocks and living organisms the fingerprints of countless stars before us. The silicon in the sand, the phosphorus in our DNA, the sodium and chlorine in the oceans. Those atoms were fashioned long ago in stellar furnaces and then scattered across space, eventually to become part of this planet. The heavy elements from bygone stars now circulate in our blood and build our cities. We truly are a way for the cosmos to experience itself, as one great scientist put it. When we gaze at the stars, we are literally seeing our own origins. The light from those distant suns allowed Earth to form and life to develop, and now our eyes capture that light and our minds understand it. We have closed a loop in a sense. The stars made us, and we in turn can comprehend and appreciate the stars. It's a humbling and uplifting realization that underscores the unity of everything in the universe. As our journey through the lives of stars comes to an end, picture yourself once more standing beneath a clear, dark night sky. The silence of the night is profound. The only sounds might be the wind or a distant owl. Above, the stars sprinkle the heavens with their gentle light. The Milky Way arches overhead, a faint band made of the amalgamated glow of billions of distant stars. With the knowledge we have gathered, each point of light now carries a story. You can point to a star and think, that might be a middle-aged star like the Sun, with planets orbiting it and perhaps life of its own. Another might be a massive blue giant destined for a short, brilliant life and a dramatic supernova end. That red one there could be a giant star in its final phases, about to shed its husk and reveal a white dwarf. Yet another faint smudge might not be a single star at all, but an entire galaxy far beyond our own, filled with hundreds of billions of stars, each with its own journey. In the stillness of such a night, the weight of this understanding can be awe-inspiring. We stand tiny on a small planet, bathed in the ancient light of stars, connecting us to epochs and places we will never see. The stars evoke not just scientific curiosity, but also a deep emotional response. For thousands of years, humans have looked up in wonder, weaving myths and seeking guidance from the stars. In ancient times, the night sky was humanity's map and calendar. Farmers planted and harvested by the rising of certain stars. Sailors navigated by the star patterns, and every culture filled the sky with stories, images of bears, hunters, dragons, and heroes that gave meaning to those distant lights. The stars have always been our companions in the dark, symbols of permanence, even as we now know they too have life cycles. Now we have peeled back many of their secrets, yet the wonder remains, and has perhaps only grown deeper. We know that those stars are not eternal. They are born, they age, and they die, in an endless cosmic cycle. We know that on some nights, some of the stars we see have already died in reality, but their light is still on its way to us, a messenger from the past. We know that every atom in our body was once inside a star that died long before Earth formed. We are intimately connected to these points of light. They are our stellar ancestors, and in a real sense, we are their children. Such knowledge does not diminish the star's beauty, it amplifies it. When we look up now, we see not just pretty lights, but a grand story unfolding across the vastness. Eventually, even the stars will fade. The universe is dynamic and evolving. Trillions of years from now, the galaxies will exhaust their gas, star formation will cease, and the remaining stars will gradually die out. The cosmos will go dark again, as it was in the beginning, but now filled with the remnants of those stars. White dwarfs turned cold and black, neutron stars, and black holes roaming the darkness. But that far future is almost beyond contemplation. Right now, we live in a universe awash with starlight. It is the golden age of stars, where new ones still form and the night sky still gleams. We are fortunate to witness it, and as long as there are eyes to see and minds to wonder, the stars will never be merely points of light. They will be beacons of meaning, symbols of the enduring cycle of creation and transformation. Stars are the ancestors of everything we know and the architects of the universe's structure. They crafted the elements that form our world and our bodies. They organize themselves into galaxies that shape the cosmos on the grandest scales. As we conclude this meditation on stars, we find ourselves back in silence, contemplating the darkness that is now no longer empty. It's filled with the gentle glow of distant stars and galaxies, a cosmic tapestry woven by countless suns. In the great silence of space, the starlight we see continues to journey outward. Even after a star has lived its life and gone, its light remains, traveling through the darkness, carrying the tale of that star's life to faraway places. Right now, above you, photons from stars hundreds of light years away are gently landing on your eyes, having left their homes long before you were born. And those photons will continue past you into the night, on an endless voyage. The universe is silent, but it is not empty. It is filled with the stories of stars, whispered in the language of light. And so we end where we began, with darkness and quiet. But now we know that in that darkness, light is always traveling. The stars, our brilliant ancestors and cosmic architects, shine on, and in the quiet darkness, their light continues its eternal journey. In the silent darkness of space, their starlight continues to travel, carrying their story across the cosmos forever.